Hello?
Oh, hello, can you hear me?
Yes, of course. How are you doing?
Okay, I'm doing okay. My computer is not doing okay.
Oh, feeling
Yeah, I
feeling the
can.
same. Today my MacBook Air is died, bricked, I can say, because the screen itself is not working.
Uh-huh.
So if you plug in
Yeah,
HDMI and close the laptop itself, it can work, but actually without the external screen, this laptop is useless now.
I see.
So,
Yeah, I have two issues actually. My monitor is shaking on its own for
uh-huh.
some reason. I don't know what's happening. It says optimizing screen. It does that, and then it does that again after like 10 seconds.
Okay,
So, so
that's
yeah,
bad.
that's one thing. And the second thing is that my Wayland system does not recognize my microphone. So
Ah,
yeah.
okay, okay. I get it. I had the similar issue with Wayland, but not microphone.
Mm-hmm.
It was just my headphones,
I
which
see.
are plugged in via USB driver from the Razer itself. So they have some
I see.
trouble recognizing them. But I don't remember how actually I've managed to fix it, but now it works.
Yeah, Linux is a series of tricks, really.
Hi. Okay. So,
Yeah, Kai said he's going to be a bit late.
uh-huh.
So we might as well get started. Um,
Yeah, sure.
let's see. Yeah, because I really wanted to share my screen today, but
Mm-hmm.
so this is the weirdest thing. Like until today, my X window manager was working. I
Uh-huh.
didn't have to use Wayland, but
Mm-hmm.
for some reason I cannot log into it today. So
Uh,
just
are you using some kind of SDDM or like similar thing to log
yeah,
in? Uh-huh.
yeah, it's SDDN. Yeah.
So what DMSG command says that it has some kind of issues with X11.
Hmm, let's see.
Usually I try to boot in X11, and then if I have some troubles booting or logging in, I just can switch to the next TTY with
Right.
yeah, Control Alt and
Control Alt
F3,
F1. Yeah.
F1, F3, and then log in and type dmsg command.
Yeah, let me try this for the last time. If it works, it works.
Yeah, why not? Take your time.
Oh, it works. Wow. Okay.
Cool.
Okay. Wow, you're lucky for me. Seriously. Yeah, because until now it was not working.
Yeah, that's cool. Actually,
Because it just gives me
I've
uh-huh.
tried to read the 1.9 normal forms and confluence, and then tried to read fixed point theorem and etc. But
Mhm.
actually, I've not understand that much.
Yeah, okay. Okay. That's fine. Yeah, so we will have to take things a bit slow Yeah, I was just going to say more about this. So that the main thing in this chapter,
Mm-hmm.
like of what is left in the chapter, is actually a theorem of which they did not give a proof. That's the Church-Russell theorem.
Mm-hmm.
Um, so they don't prove that theorem because they say it's too complicated, blah blah blah. But instead they prove like a corollary of the theorem, um, an extension of the theorem. So what I was thinking is, so there are two ways we can go. We can go with the authors and we can just ignore the proof, but or we can just take a kind of detour and understand George Roser well, and then continue the book. Because the thing is, George Roser is like fundamental to type theory. It's the bedrock on which everything else resists. Like whether it is homotopy type theory, whether
Mm-hmm.
it is like what goes on in Lean, like much of that is built on church author. So being able to do that proof, I think, will be a good idea.
Yeah.
It can be very complicated
Uh-huh.
because just realize that these authors themselves did not include it because they thought it was so complicated. Um, so what I was thinking is according to how you like, because I have seen this proof like a few years ago, so I totally have forgotten it, but I want to do it again.
Yeah, why
So,
not?
but that's me personally. I don't want to drag you guys along if it's too boring or it's like it's too much because it is too much. So yeah.
Yeah, why not?
So
If
what I was
it's the
thinking is,
fundamental and it
yeah,
played the under as a fundamental to all of the future topics, I think we need
mhm.
to dig down, dig deeper. Yeah.
Yes, yes, yes.
And then I've
Because
read a bit the simple type lambda calculus, few chapters.
yes, yes,
Uh-huh. That's cool.
yes, yes, yes. So that's what I was thinking is we do church roster because so what we can do is today it depends on what you and Kai feel, obviously. What I was thinking is what we do today is we do everything except church roster. So like the beta normal form, and then there's the fixed point theorem. Those are like things we can tackle. Like this compared to church roster, they're like doable.
Mm-hmm.
So what I was thinking is we do that, we finish everything that's in the book, and
Mm-hmm.
then next time we start with a church roster from scratch and like understand that theorem very very well.
Yeah, I think that's great. Let's stick with the easiest chapters first, and then wait for
Yes.
Kai, and then we can spend all the next hour meeting discussing only charge rose theorem. Uh-huh. CR.
Yes. 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 Yeah. Um, so yeah, that will be better because what we can do is, well, we can just finish the chapters and then we can get on to the exercises.
Mm-hmm.
So we can do the exercises while we do the kind of proof work, because the proof work is just going to be like us discussing through the proof and trying to understand it,
Mm-hmm.
and just to make sure that we don't forget what we learned until now, we will like simultaneously also keep doing the exercises.
Yeah.
Um,
Actually, I've done with Kai some part of exercises. So
okay.
let me check. I've Scully draw. Scully draw. Ah, yeah, yeah. Here we go. Here we go. Wait a minute. I can share my screen. Share screen. this, no, this one. Mhm.
Okay.
Yeah, we solved. Actually, up to this one, I guess we solved some
Okay. That's
exercises.
cool.
Yeah, I have a lot of notes, and then we discussed how to simplify and better reduction, I guess. Which one? So these the later topics. Yeah, up to the
Mm-hmm.
1.5, including 1.5, we've done these exercises.
Okay.
This was very easy, and then yeah, that was two identity. Yeah, identity functions. Yeah, that was, yeah. I started marking the x's with 1, 2, so we can split them and not mess with them.
Uh-huh.
And then
Sure.
some trees. How this were called? Wait a minute.
Yeah, the lambda trees, yeah.
Lambda trees, Yeah. 1.3.6. No. Yeah. Figure 1.1. It's a lambda tree. Then alpha conversion, alpha equivalence. Prove that.
Yep.
So actually, we didn't prove. Just write down by intuition and look for
Mm-hmm.
some references in book, but without actual proving.
Okay.
Okay, it's on the term. I guess we did this too. Okay. So yes, we can just follow the. I guess we left on beta reduction previous time.
Yes.
Wait a
Yeah,
minute,
like
it was.
beginning of better reduction.
We we use substitution. We used substitution inside beta reduction. I remember. Yeah, we substitute
Yes.
variables with a new one,
Yes.
generally called beta reduction. Yeah, I remember that. And then we left on this. Which one? Wait a minute. Wait a minute. It's better to look at the book. Yeah, we were discussing the order of operations, order of redexes. I remember.
Right. Okay, I'm going to join from my computer and
Okay.
see how it goes. Okay.
Okay.
Give me a second.
No problem. Take your time. Здорово, здорово, Камран, как сам? Да, теория типов. Вот эта книжка.
Hello, can you hear me?
Я.
Yeah, okay. Yeah, I don't think the computer thing is going to work. Yeah, so what we can do is, yeah, you use Excalibur, right?
Yeah. For
Yeah,
the
so what we can
notes.
do is we can just, yeah, we can have a shared
Ah,
thing, and I guess we can,
that's great. Great idea. Wait a minute.
yeah, if we can create one and share a link, that'll be great.
Ah, yeah. So session. Wait a minute. This one.
Yes. Yeah, let me join.
Mm-hmm.
Yep, can you see me?
Yes.
Yeah, okay. All right. Yeah, at least this way we can draw and communicate whatever we want.
Mm-hmm.
Cool. So we can just start with
From better reduction from the start all over again. Maybe just to
sorry,
make.
I could not hear you again.
Ah, I mean, the chapter of beta reduction from the start, you mean? As a
No,
refresh.
not from the start.
Ah,
No.
okay.
We stopped at one place, right? I think we should start from the double beta reduction. Look, there's a beta reduction relation with like a double arrow. We
Uh-huh,
should
uh-huh.
start from there. Yeah.
Zero or more step, yeah? You mean this one?
Yes. Yes.
Definition
Yes. Yes.
1.8.3. Mm-hmm.
Yes. 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 Let me get my PDF ready. And by the way, Kai.
I can't hear you. You have
Okay.
issues with
I was
microphone.
saying.
Uh-huh.
Can you do you have an idea about when Kai is going to join? Should we wait for him?
Um, wait a minute. I tried to call him, but actually I don't know
Okay.
his mobile phone number.
Okay.
What? I think he's offline right now. I can't
He is?
communicate with
Okay.
him. So we can basically
Okay.
start, and then if he manages to join, we can continue with him.
Sure. Yeah, I just wouldn't want him to, like leave him. So that's
Mm-hmm.
yeah. So okay, if that is clear, then I guess there will be a recording, right? So he can always
I am
see in
recording.
the
Yeah,
recording. And
we are live.
okay, okay, we are live. Okay, okay. So let's start with one point, that one or more definition. Huh? That'll be good. Okay. Okay, so what I'm going to do right now is I'm going to uh, like take this definition, a screenshot of this, and put this on the writing pad.
Mm-hmm.
Yeah, let me do that. Yes, do you see this? Well, you did already.
Okay, okay. The photo version
Yeah.
is better. Yeah.
Okay. 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 So yeah. So what this is saying is basically is that we already understand what beta reduction one step is, right?
Mm-hmm.
It's just that for every abstraction, you try to take the n or the thing that you're applying it to and then replace it with every free occurrence
Mm-hmm.
in m, right? That's
Mm-hmm.
the one step beta reduction. And what this zero or one more step is saying is that we are going to do this single step beta reduction for a series, right? So we're going to have, so I hope this is how we write. Yes.
Mm-hmm.
Where's the undo? Control Z is the undo, right? Yeah.
Yeah.
Okay, so we start from one place. So this is M0.
Mm-hmm.
And this M0 or M naught is going to be equivalent to just M.
Mm-hmm.
Okay. And then we're going to create these repeated beta reductions. So M0 gets reduced to M1, M1 gets reduced to M2,
Mm-hmm.
and so on until we have Mn minus 1, which gets beta reduced to Mn,
Mm-hmm.
right? And this Mn is just going to be N. Okay? So we have this
Okay.
long reduction, which
Uh-huh.
like so it's like syntactic sugar, right? So this thing is the syntactic sugar for these things, right? um
Yeah, let's make
so
some little example if you don't mind.
sure,
So if
sure.
we have say have let's say it's this way, and then we have
Mhm.
and then we apply. I guess we can apply like this one. Yeah, am I right?
Mhm.
So in the end, it will become. So the first step, we start on the wrap. So we can say that this one is the 0th one, or it's M,
Mhm.
and then we stop
Mhm.
unpacking. Okay. So
Right.
that mean we have we end up with, we apply the 2. Am I going right?
Yeah. Yeah. So basically, we can say that, yeah, this is M1, this gets reduced to this, and then it will be reduced again. Yes.
So we can say that's the M2, and we end up with 2 plot 3, or no,
Yeah.
just 5, I guess.
Yeah.
Yeah.
Right. So that's basically the. So the interesting thing is that, okay, then you'll ask, if we already had single step reductions, why do we need this chain, right? It's like we knew what to do in reduction, and we can just do that repeatedly, right? But why this new arrow? So the reason is that, um, we have this new arrow that says that M has a particular relation to N. So this thing is actually a binary relation. Okay?
Yeah.
And because it's a binary relation, it's going to say that these two things are related in some manner, right? So consider it like it's like an abstraction, right? It's like we have beta reduction, which reduces one thing from another, but we are not just satisfied with functions. We want to say, if we have these beta reductions, then what can we say about these two things as property, right? So binary relation, this double arrow is almost like a property, just like, alpha conversion is a property. This one is also a property in the sense that this says that M can be reduced to N, right? Or M has this beta reduction relation to N. Okay. So that's kind of a better way to read it, is that M has a beta reduction relation to N. And how do you verify that this relation exists? Well, you just prove that these functions exist, or these beta reductions exist.
This
right? If you can
chain,
show
actually,
that, yeah, if you can show that this sequence, this chain exists, then M has a beta reduction relation to N. Okay.
Okay. Let's think. So the definition says that it can be equal to 0. So we can have some lambda term, or just basically the variable a. It after all the beta reduction, it says it stays as a, because we cannot reduce it anymore. So
yes,
it has M0 and it has 0 ends. So it ended up with M0, I can say.
yes. So that's why it says, right, 0 or more step. So you can have 0 step.
Yeah.
And 0 step is just basically, it's like saying that like you cannot reduce it anymore.
Yeah.
Right. Yeah. Okay, just give me a minute. Yes, so that's what you should think about it. Like, it's a binary relation, and the binary relation aspect is important when we will do the when we will do the Church-Rosser. When we will do the Church-Rosser theorem proof, this thing is important.
Okay.
So yeah. Yes. So yeah, I think we already saw this example that they give. Um, this one, um, lambda x dot lambda y dot x
Mm-hmm.
z v, right? Um,
Mm-hmm.
so we saw how it can be reduced. Like if you reduce the outermost one, you get something, and then you reduce the innermost one, you get something, right?
Yeah.
Um,
Mm-hmm.
so we can say that for this term, we have two chains,
Mm.
right?
Two
And
roads.
both of those
Uh-huh.
yes. So both of those chains actually lead us to ZV,
Uh-huh.
right?
Uh-huh. Uh-huh.
Uh, so what this means is that this lambda term has a beta reduction in relation to ZV in two ways.
Mm.
You
How
see, so
can we represent this kind of statement? It's like this one. I mean, we have two ways. How can we represent the two
yeah,
ways?
well, the two ways is like you have to just write down the two chains, right? So it's going to be lambda x dot lambda y dot yx z v gets beta reduced to, you do the outermost one, so
Mm-hmm.
you will have a lambda y, uh,
YXV.
yes,
Mm-hmm.
zy v, or yz.
Uh,
Sorry, it's going to be
yeah, yeah.
yz.
Uh-huh.
Yeah, yeah.
YX V. Uh-huh. Uh-huh.
Yeah,
Yeah.
x is going to be replaced by z, so it's going to be yz v. So that's what it reduced to, and then you can reduce it to zv, right?
Wait a second. Wait a second. So this gonna replace X, and it will be this way. I can say that that's it. This is the V and Z, and then we
Yes,
came
yes,
to ZV.
yes,
Uh-huh. Yeah,
yes, yes. Yeah, yeah, I had it the other way.
it's okay.
Yes, so this is one way to get to ZV, and then you do the inside one. The inside one is, I think I wrote the inside one.
Mm-hmm.
Yeah. So this gets beta reduced to, so you do the inside one. So
Yeah,
this
yeah.
is,
You wrote the
uh,
inside one.
uh, so yeah, what I was saying. This is lambda x dot. This is going to be yz.
ZX.
Yeah, sorry, zx. Yeah, so this is going to be zxv. That's just zv. Right. So these are the two chains that lead us to zv. Right.
I
Um,
got the point that if we write the relation as this symbol, beta, we should specify all
mhm,
the chains by one. So whereas we can write the double arrow
mhm.
specification and go straight from 0 up to the nth one, where we
And
can
yes,
stick with n plus 1 here, basically.
yes, yes,
So we cannot jump
yes.
from n to n
Mhm.
using this how can I say, definition or description
Map. Yes. Yeah.
symbol. Uh-huh.
Okay. So yeah, that's pretty much what it is. It's just like an abstraction of many beta reductions. Um, Yeah, so there is this lemma 1.8.4. Let's go through that. It just proves certain properties of this beta reduction relation. I'm going to copy this thing onto here. And how do I move this? Yes. Okay, so what does it say? It says that this beta reduction relation extends the beta reduction band. That is, if M is beta reduced to N, then M must also has the beta reduction relation to N.
Yeah, that makes sense.
Right. So how can you do that? You just take N equals to 1. Right? If it's N equals to 1, it's just one map, and it means that if M can be beta reduced to N, then it also has the beta reduction relation. So, right? So we'll write that 1, it's just the case when N is equal to 1, M beta reduced to N implies M has a beta reduction relation to N. Okay, so that's the trivial case. That's the N equals to 1 case. Now we have to show the second thing the lemma says is that this relation is reflexive and transitive.
Reflexivity.
So you remember what is?
Yeah.
Yes. It takes
It's
it to
basically
itself.
plus zero.
Yes. And then we have to show that it's transitive in the sense that it can take 3 things, and it's associative basically. Yeah. So how do we show reflexivity? Well, reflexivity, I think we already talked about this. It's just N equals to 0, right? It takes it to itself, right? So for N equals to 0, M gets reduced to itself. Okay, so what this means is that M beta reduced to M. And then we can use the previous one, right? The previous lemma that we just proved for N equals to 1, because this relation extends this, we can say that if M can be beta reduced to itself, then M must also has a beta reduction relation to itself.
Yeah.
Okay, because this single arrow holds, and we proved that single arrow holds implies double arrow holds, so we can just say that M has double arrow beta. Okay, that's what it is. Then we have to show transitivity, right? So this was reflexive. Now we have to show the transitive property. Yeah. How do we do the transitive property? Do you have any idea?
Actually, I'm not good at proving, but I remember some things on the chapter. Wait a minute. Remember.
Yeah, you don't have to think about proving. You just see what you're given.
So
right?
if we can 1 plus L, if we can have beta reduction relation from L to M, and we have beta reduction from M to N, then we have beta reduction relation from L to N.
Yes.
I mean, it's obvious, but In terms of proving,
Yeah. Okay, so let me show how we can go. So like the interesting thing about mathematical proofs is that you start by just declaring. And this is where like something like lean or like in
Mhm,
functional programming we say declarative style, right? We just declare what exists, right?
mhm, mhm.
So we are given. So this is given, right? So we are given that. Write it like this. So we're given that L has a beta reduction relation to M. Okay, so now we say, okay, now we declare, what does that mean? Well, that means that for all I in 0 to N, so it's just less than or equal to, greater than or equal to 0 and less than N.
Mhm,
It's
mhm.
just mathematical symbol for that. So for all i's in from less than greater than or equal to 0 to less than n, we have let's say we have L and N taken some x, right? Some x's from 0 to xn, such that um, we have L equivalent to x0 gets beta reduced to x1, gets beta reduced to x2, gets beta reduced to xn minus 1, xn, which is equivalent to m.
Can I
That's what
ask,
this means.
why should we describe the n minus one element?
Why do I write this one?
Yeah. Why
Yeah,
can't we just write xn? It reduced to xn.
it does get reduced. So xn minus 1 gets reduced to xn. I'm just showing that before xn, there is xn minus 1.
Uh-huh.
So it's like a chain, right? So like I'm showing what is before and then what gets shown.
Yeah,
So
it's
so this is
incrementing by
xn
step
minus
one.
1.
It's incrementing by step one.
Yes.
Uh-huh.
Yes. So L beta reduction relation M means this whole thing, right? Now we can say that, okay, so this is true. We know this is true. Okay. Now we see what else are we given in the statement. We say that M is also beta reduction relation to N. Okay, so we write that down as well, right? So we have M beta reduction relation to N, right? So again, we have the same definition for all I, or we can, well, no, it's I. So from 0 to N, we have, what is it? We use x's, we can use yn, such that m is equivalent to y0, beta reduced to y1, beta reduced to y2, continues until beta reduced to yn minus 1 is, what is this, n. Okay? Do you get this?
Yeah, I get that.
Okay.
But
Okay.
it's just mathematical for loop.
Yes.
This condition side.
Yes.
Okay, but so we kind of describe that we start from 0 and up to n because we introduced this limitation here, and then
Mhm.
we say that L is equivalent, yeah,
Mhm.
to
Mhm.
x0, and it can better reduce to x1 and then x2 and up to the n. And
Right.
the latest state is m. Okay, I get this one.
Okay.
And then we describe the double, not the double,
Yes.
better reduction how can wait a second. Beta reduction
Relation.
relation. Beta reduction relation, because it is the same as the beta reduction. The relation is the same because it implies the beta reduction itself. So we can say that the second we write the second statement definition
No, so
is equal.
right. No. So what we have is, so here L is beta reduction relation to M. Here it is M to N. Right. So we have two statements. So look at the proof.
Yeah.
So for all L, M, N, if L is beta reduction relation to M and M is beta reduction relation to N. So we're just like writing that out, right? So we have the first one, this, and then we have the second one, this. We're just like expanding the definitions, right?
Right.
Okay, so we know that these two statements are true. Okay. Now we have to show that this statement is true, right? So we have to show that what is it? L can be related to N. So we have to show that L has a beta reduction relation to N. That is for all I, again, from 0 to N. For Z0 to Zn, we have Z0 equivalent to L, beta reduced to Z1, Zn minus 1, Zn. Right? And Zn is equivalent to N. Okay. Now, we have to show this. So this thing, we don't know whether it is true, right? These two statements, we know what is true. So it's pretty much like induction, honestly. So if you see these two statements, what's interesting about them, right? What's interesting is, okay, we have this chain of x's that take you from L to M. Okay. So you say that L is equivalent to x0 and M is equivalent to xn. So, and this equivalence, remember, this equivalence is lambda alpha modulo equivalence, if you remember what we talked about, the big lambda, the classes, right? So this is alpha modulo equivalence. Basically saying that they're like syntactically same, right? So they can be
syntactically equal.
very equal. Yeah. So if xn is syntactically equal to M, and then in the next statement we're saying M is syntactically equivalent to y0, then we can say that xn is syntactically equivalent to y0.
So we chain the xn with y0.
Exactly. So you see, so we get a snake. We get a snake that comes from here to here and gives us n. Okay. So how do we write this in terms of proof? Well, we just say that as per what is it? Alpha modulo equivalence, M is equivalent to xn and M is equivalent to y0. Thus, x is equivalent to y0. Sorry, xn is equivalent to y0. So
Yeah.
Okay.
Therefore,
so that's the first thing. No, we're not done yet. So xn is the same as y0, right? And then we say that, what is it? Where did I lose? Yeah, here. So we say that yn is equivalent to n, right? Yeah. And here we say that zn is equivalent to n. So obviously yn is equal to zn, right? And here we say that L is equivalent to Z0 and L is equivalent to X naught. So Z0 is X0. Okay. Okay. So now if we take all of that into account, okay. So you see we're starting from Z0, right? And everything that we're making equal to is actually the same. You see what's happening here?
Yeah, we
Yeah.
it's specifying. Can I show you? So we have first we have m to n, which is x0 to xn, and then we have n to l. Yeah, right? Sorry.
Yep.
L to m. Wait a minute. You have L to m, and then we have m to n, which is y0 to yn, and now we're specifying L to n, which is L is equal to z0 to zn, but we can specify that z0 is actually x0, and then the middle part one xn is y0, and the n zn is yn. Therefore, so yeah, we have two ranges, and then we chaining them.
Yes.
Yeah. Yeah, intuitively it's very obvious, but now I get how it is done mathematically. Proven.
Yes. So you state what you already know, and then you proceed. So it's like you state what you already know, and then you figure out, okay, what I already know also has something else that I did not think I knew. And then you use that new thing to show that this can be proven. So we say that xn is equal to y0, and then we can just say that these two chains can be connected, and because these two chains can be connected, L has a beta reduction relation to n. Yeah, that's pretty much it. I think one exercise could be just to, I don't know, write it down on pen and paper and think through it again. It's like, just doing it again and again. You'll get the feel of it.
Can we also say that L is beta reduced to n? Not relation, but just one arrow.
No. We cannot say that because L gets reduced to something else, right?
In this particular example.
Right. So it's like if we go back to this example that we just did, here in the first one, we get reduced to this one, right? So So we can say that this lambda term is beta reduced, single beta reduced to this. No, this lambda term is single beta reduced to this or this, right?
Mm-hmm.
And this gets single beta reduced to this,
Okay.
right? So it's like saying, what is it?
So yeah, we're
Um,
referring to this table where
yeah,
we say
yeah,
that
yeah,
with single arrow we represent the singular step, whereas
yes.
with double arrow. And one more interesting question: can we say that n0? Can we describe n0 beta reduction with one arrow?
Mhm.
It's not relation. I mean this one reflexivity.
Yeah, so yeah, that's the reflexivity, right? That's when those two arrows are equal. You can use those two arrows interchangeably,
But what
right?
about with one arrow? Just one arrow beta reduction.
Yeah, that's true.
Is it
That's true.
applicable?
Yeah,
Uh-huh. Okay. Okay.
yeah, yeah.
Cool. 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 Cool.
Yeah, I guess we already have Kai. Hello, Kai. Sorry we started before you.
So sorry, I'm interrupting you. I mean, this statement is the end of proof. Yes, right?
Yes.
So it specifies that m is xn and m is xy. Ah, yeah, yeah, yeah. This is the chaining thing.
Yeah. So yes, you connect the two chains, and then you can say that you have a chain that is made up of the other two chains.
Mm-hmm, mm-hmm. And these statements is crucial. So we should
Yeah.
get and show this thing, the connection thing. Okay,
Yes.
okay, okay. Thank you.
Yeah. So it's like it's an algorithm, right? You start with stating what is true, and then you state what needs to be true, and then you look at what is already true, and you figure out, okay, how can I make something else out of it? And then
Mm-hmm,
you show it.
mm-hmm, mm-hmm.
Yes.
And
So yeah, we're now.
can you
Mhm.
say how this form of proof is called, named? I heard that.
It's
Uh-huh.
it's inductive.
In by
It's
induction.
induct.
Uh-huh.
Yeah, by induction in the sense that you already know truth is for like some things are true, and then you want to extend it for other things, so you make a proof that shows that yeah, it can be extended. So that's what we did, right? So we knew that these two things are true, but then we extended it to saying that this can also be true. That's induction.
Okay. Thank you.
Yeah. Okay, so that's the whole beta reduction relation. Actually, you can actually extend this beta again to make it an equality, like we had alpha conversion. We can also have beta conversion, right? So that's the next definition. Yeah, but also I wanted to ask Kai. You just jumped in. Any questions? Anything?
No, everything was understandable. I've been listening for like 5 to 10 minutes or something at this point.
Okay.
Yeah, I read it by myself, so yeah, that was understandable. No questions left.
Ah, cool, cool, cool. Yeah, let's do the beta conversion one. Let me paste that uh, definition. Yes. Yeah, so basically this is like alpha conversion, but it's for beta reductions, right? So I think you might have already gotten like an idea out of it. So what we do with this alpha and beta stuff is we first declare a relation. It's like a binary relation that relates two things, and then we build some sort of more powerful relation. So we had like beta, and then we built this double arrow beta, and then we build an equality of these two things, right? So this is just binary relation. It has no special properties. This has reflexive and transitive property. This has reflexive, I'm just writing like a monkey, and symmetric properties. So these are like special kinds of binary relations. So this is like your very naive binary relation. This is more powerful, and this is the most powerful. This is called an equivalence relation. Equivalence relation are like special types of binary relations. A function is usually an equivalence relation. Now, a bijective function like an isomorphism is an equivalence relation. Basically, the idea is you construct a binary relation and then you give more power to it. More power means more properties that are true. Right? We did that with alpha. You see, we had like renaming. So renaming was like the lowest one or like the least powerful. And then we had alpha conversion, and then we had alpha equivalence, right? So yeah, and this thing is the same thing. What this thing does is it says if two lambda terms can be reduced to each other, right? So what this means is that if you have m and if you have n, you can beta reduced one to the other one in any direction you want, either from left to right or right or left. That's what the conversion says, is that you have chains that go in either direction, either from m to n or from n to n. And if you have either of them, then they're beta convertible or beta 2. Does that make sense?
Yes.
Does.
Yes. Yeah. So the old example again, we had
So I'm
lambda
still
x.
sorry, I'm still curious how
Go ahead.
n can be backwards chained such that we can transform it from n to m.
It's the same thing, right? So you can have, let's say,
We have
you know,
let's take the previous example with wait a minute. Um, yeah, I copied the same thing. So we ended up reducing this lambda term to zb,
right.
but you said that we can do the backwards. For example, but actually we can do this thing, for example. Uh, can it be reduced to the nothing, or
No.
how? To, for example, to arbitrary. because we don't use the y, so it can be better reduced to zv. So we can. So if we take this lambda term, it can be better reduction relation with two ways,
Yes.
either inner or outer
Yes.
ordering. But the backwards, if we take the from n to m, we end up with endless, almost infinite amount of lambda terms. So you can write anything you want. The only thing to satisfy is it should give back zv, or if we think two distinct variables, so they are actually alpha equivalent with ab, for example, because they have no meaning at this stage, just two variables. So we can say that anything that returns two distinct variables is equal, is not symmetrical, not symmetrically equal. Triple. This called, you said, the alpha conversion. Yeah. So, for example, beta. Okay, I'm thinking too much. Okay, let's continue our.
No. I think you're on the right track. The only thing is that if you take the same example, right? So we have, let's say, the set of four things, right? You have this, the whole term itself. You have this. Then you have the what you get after inner and outer. So those two things. So we have lambda y dot yv x, sorry, z. Then you have lambda x dot zx v, sorry, v, and then you have just zv. So this set that we have, so these are the four things that are like involved in the chains, right? If you look at this, what we can see is that, for example, these two things are beta equal to each other. How? Well, we can just have lambda y dot yv z. Oh, this is happening. Z beta reduced to zv, and we can just write this. You see?
Right.
Both of them are.
What
So
about
what we did.
if the, sorry, I'm interrupting you. What about if we have a term that return not z and v variables, or we apply to z, yeah, or z apply to, no, we apply to z, and we have the term lambda term. It's identical to this one, ab. Is it beta equal to zb in this
If
particular?
No, okay, so if these two things are equal, right? That's what you're saying. You can reduce this to this, or something like that. And because we already know that this can be reduced to this, then yes, obviously they're equal. Yeah.
Okay,
So
thank you.
they're equal.
Thank you.
Basically, you need to ensure that so it's like A has to be beta equal to B, and to do this, what you need to show is that there's a chain that helps you convert one to another. There's a chain that allows you to, or like you can say that there's one common term that allows you to go from that term to both the places. So yeah, so it's the same thing, right? So if you write down the original one del y or yx, z, v, you can write it like that, right? So this gets reduced to yvz, and this again, on the other hand, gets reduced to lambda z, sorry, x, zx, v, right? So these two things are the same. This is one chain, this is another chain. The middle term is different, but that doesn't matter. You just need one way of connecting these two things. Does that make sense?
Yeah, that's clear and clean and cool.
Okay.
That's the beauty of
Yeah, so
mathematics.
that, yeah, certainly. Yeah, that's what beta equality is. It's just your ability to say whether using beta reduction you can make things equal, right? Yeah, and as I said, this beta equality is actually very special because it is an equivalence relation, right? And we have to show that it is an equivalence relation, which means that we have to show that it is reflexive, transitive, and symmetric. And that's what the next lemma is about, I guess. Yeah.
One more thing. Let's do a quick recap. So we have this which is not equal, for example, for this one, because they are not syntactically equal, but semantically they're equal. So that's why we can say that they are alpha equivalent.
Yes.
And also they are beta equivalent. But
yes,
we have an issue like this one, for example. We have yv and z, which, and also we have a lambda x, z x, and v. They are not alpha equivalent, but when we reduce them, they are equivalent. Am I right? Am I on right track?
yes, they're
So
beta equivalent.
the
Yes,
3 levels of equivalency, we have syntactical
yes,
and semantic, not semantical, positional, I can say, because their positions are the same, but they have different variables. But and we have the third one, which looks like completely different thing, but if you reduce them to simplify them to the simplest form, they are equivalent. It's kind of beta reduction is powerful, but equivalence and alpha equivalence, and then have syntactical. Yeah, I'm done. Sorry.
No, that's good. This is good. Yeah. Okay. Yes. We now have to prove two things. Yeah. Let me copy paste that. Yes. Yeah, so the first thing is the same thing as before. You need to show that the equality extends the beta reduction relation, and you can do it just like the last time. Uh, yeah, it's just case n equals to 1. Um, if m has a, so if I have to write, if m has a beta reduction relation to n, then for all I in we have this chain. Now what this means is that if we consider n equals to 1, then there's just one thing between them. So n gets beta reduced to some x, and then it gets beta reduced to x. Or they're equivalent, beta equivalent. So that's the extension. It's just the definition. The second one is interesting.
Wait, sorry. You mean that if we have, we can reduce m to x, beta reduce, and then beta reduce x to n? You said that. Wait a second. I don't see here the backward relation.
Well, we don't necessarily need the backward relation. We just need to show that like there exists a chain from one to the other way. So if we go back to the definition, it's just that the example we chose had a very special backward relation thing in both the direction, but that's not necessarily the case every time. So if you come here, if you look at this, it says that m is beta equivalent to, or beta equal to n. If there is an n greater than or equal to 0, and there are terms, yada, 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 for such that either there is mi beta reduced to mi plus 1, or mi plus 1 beta reduced to mi, right?
Yeah, here's
so
the backward thing.
Yes. So there's either or. It's not like you need both.
Okay, I got you.
It's just that our special example had both. Yeah. So it says know that each pair of mi and yeah, be related by the single step relation, but not necessarily from left to right. It may also happen that some of these pairs are related the other way around. So the direction does not matter. You just need a chain. Yeah, going back to the lemma. The reflexive properties is pretty straightforward. It's just the case n equals to 0. So it has n equals to 0. That means m has double error relation to itself. That just means that there exists a chain, and that means and is also B-type equivalent to itself. So yeah, that's just the trivial case. Yeah, for symmetric property, we need to check, right? We need to see if m is beta equal to n, then n is also beta equal to m. That's why this is an equality, right? The equality holds in both orders. If you change the order, it still holds. And this is easy, right? So
Yeah.
we say that it.
Sorry, but here's
I
the
don't think.
trick.
Mhm.
Here's the trick with the either thing. Wait a second. Wait a second. Wait a second. We have the this thing. So in this definition, we say that we have the either forward or backward. Yeah.
Yeah.
How it can be chained with symmetry. I'm saying.
Okay.
So if we say that if we have mi to mi plus 1, how it can be equal? Wait a second. I mean, this one. If we here say that we can have one thing at a time, not necessarily both at the time, but one of them, how can they be symmetrical?
But we don't want this mi's to be equal though. We don't want them to be equal. We want them just to have a chain. We want the thing that they're chaining to be equal, right? So so the idea
So
is
that
that
the source and destination, the equality between the source and
yes,
destination,
Mm.
not necessarily the arrows.
yes, yeah. So the destination must be equal, but what source you take or like what paths you take doesn't matter, right? So if m is beta equal to wait, are you able to see my drawing? Yeah. Yeah, if m is beta equal to n, then what does that mean? That implies that there exists a chain such that m0 can be beta reduced all the way to n, right? That's what it means. M can be beta reduced all the way to n. That's what it means. Now, the thing is, because this is true, and then we want to say n is beta equal to m, we need to show that there is a chain from n to m in either direction. You see? So we already know. Okay, I think I will have to write this out because it doesn't make sense. Let me do this more explicitly. So this is what we know. And we can say that there are these MIs. So let's say, let's assume MI is beta reduced to MI plus 1. So let's assume this is the direction, left to right. Okay. So now what it means is that we have this chain that goes in this direction, very specifically in this direction, until we reach MN. Correct. Now, now if we try to invert this chain, okay, we just write it in the opposite direction. And n minus 2, so on, until we have n0. Do you get this?
Right.
This is still true. This is still true. It's just the same thing written in the other direction.
Yeah, reverse
right?
it. Same thing.
Right. And we know that this thing is n, and this thing is m. Okay. And we know that, so in this chain, what is the pattern? The pattern is that mi plus 1 is beta reduced from mi. It's the opposite of this. You see, it's the same thing but written in the other direction.
Yes.
It's literally the same thing. I've just like turned it.
So
right?
we're basically saying they have the both linkage from the both sides.
No. We're not saying anything. We're just saying that A is beta reduced to C. It's the same thing as saying C got beta reduced from A.
The reverse thing.
It's just the reverse thing, right?
Okay.
Do you see this?
Yeah, I got it.
Okay. Yeah. So because this is true, then we can say that, yeah, there is a chain from N to M. It's just in the opposite direction, but equivalence does not care about left, right, whatever. So we can say that N is, beta equivalent to M, right? So what that means is that you don't need these things to be symmetric. This does not have to be symmetric. You just need them in the opposite direction. If they are in the opposite direction, then they are equivalent. So yeah. So that's symmetric. What else do we have? We have the transitive property. The transitive property is exactly the same thing as we did in the last time. We have to connect the chains. It's you have to just show that the end point of one chain is the same thing as the beginning point of the other chain.
Yeah, right. Actually, nothing changed. Just copy paste.
Yeah, nothing changed. It's copy pasting. It's just extending, right? It's like what is true for one thing, you have to extend it to another thing. It's the same.
Okay.
Yeah, so that's with that we are done with. No, we have some extra things that it says that if M has beta reduction in relation to L1 and M has beta reduction in relation to L2, then L1 is equal to L2. Yeah, well, that's just, you can use transitive property from beta reduction relation, and then you can just extend it to beta equality. Yeah. I think a good practice would be just like you know how this works intuitively, just try to write it down for practice.
Mhm.
Yeah.
Yeah, let's think about this thing. You have beta reduction from n to n, let's say. No,
Mm-hmm.
from L to M,
Mm-hmm.
we can have, and also we have beta reduction from M to N. So we can say that we have L and M has a relation, beta reduction relation. Okay. Hmm. And if we go the same way, we have M prime, and then it goes to the N prime. They can be equal. Oh, okay. I'm just want to make a quick abstract cheat sheet like summary.
Mm-hmm.
I
Sure, sure, sure.
actually like doing these things, so you can look at the shortest cheat sheet and remember all the long talks. So
Sure.
it's my motivation. I'm just struggling how to represent beta equivalence in this in short cheat sheet in a short form.
You can just write L beta equal to N or M.
Yeah. Yeah. Mm-hmm. Beta equal to n, and also n is beta equal to L.
Yep.
But if n is all beta equal to L, we can say that can we also say that it has beta reduction relation to this one? Is it true?
If L can be okay, so you're saying if L has beta equality to N, then does it have
Mm-hmm.
this beta reduction relation?
By definition, no. If I'm correct. By definition, we can't have this. Because definition says that we have either one side or another. And
yeah, but like yeah, so well, I think it is true, isn't it? Because to show that they're beta equivalent, you have to make chains, right? And double beta or beta reduction relation is just the chains.
Yeah.
So if L is beta equal to M, then I think either of the two will be true. Either L can be beta reduced to M, or M can be beta reduced to L. I think both of them cannot or does not have to be
You know
true.
what? I think that if we don't introduce the third line, I mean the beta equivalence thing, it can't be true.
Mm-hmm.
It either it can't be true. Yeah, it's not true. But if we introduce it, we have the definition of beta equivalence. Yeah, because it clearly says that it extends in both directions.
Yes.
Okay,
Yes.
okay. So
Yes.
we can say that they are equal
Yes.
if we have the equality sign. So this means
Yes.
that we have the both true. It's like a diagram where we have this.
Yes.
But also we have the separate universe with backwards, but basically it is the same. Yeah,
Yeah.
the same thing, but reverses. Yeah,
Yeah.
it's
Yeah.
kind
Yeah.
of
Yeah.
this
So
thing.
it's like, yeah, it's like basically if you have A and you have B, right? Wait, I can't draw. Yeah, B, A, B. And so for equality, we need one chain. It can be in any direction, right? So if we have um, this direction, right? Why does it stop?
I think we have too many photos for the Xcoli draw, and it struggles to save.
Ah, are you also facing problems in drawing?
Yeah, a bit, not that much.
Okay, okay, okay. Basically, what I was saying is, if you have this direction, right? So this chain is exists. So what does it mean? It means that A has the double beta relation or double arrow relation to B beta. But if you had it in the other direction from B to A, then you can say that B double arrow A is true, right? So basically, you can go from one thing to another thing by two chains, and one of them has to be true, or one of them has to be possible, right? So,
Sorry, you're disconnected from our room. Can you refresh your tab?
okay, let me see.
Yeah. So it reminds me the did you see videos about infinity? That some infinities are bigger from another
Mhm.
infinities, or the biggest number in the universe we can think about it. So when the people start to doing calculating big numbers, they start from addition, and then the next thing after addition is multiplication, and then it's exponents, and then tower of exponents, and
Mhm.
then you chain up the next thing is the operation, where the step gets you the orders of magnitude powerful thing. I can say that it has kind of similar ideas. For example, we
Yes.
have beta reduction, but it can't be. So if we have beta reduction from A to B and from B to C, we can't just write we have beta reduction from A to C directly.
Yes.
Therefore, we
Yes.
have the beta
Yes.
reduction relation with double
Yes.
arrows. But
Correct.
double arrows has own limitation. It can't go backwards. I mean, it
Yes.
can in theory, but not for all cases. So therefore, we have beta equivalence.
Equivalence.
Yeah,
Yes.
which can do everything. Which can do
Yes.
everything like beta reduction or beta reduction relation, and the opposite side. Cool, cool.
Yep. That's like so like a lot of mathematics or a lot of logic is basically this. It's like trying to strengthen one position, and you try to prove things so that you can strengthen the position and like give it more power. Um, so yeah.
Yeah, that's the beauty.
Um,
I see the beauty, but it's hard to um, describe it.
yes, it is hard to describe. Yeah. Yeah, so we did the beta, every type of beta, right? The last one thing is the beta normal form, and the beta normal form is just like it cannot be reduced anymore. That's all it means, really. That is,
It
it's the
means
simplest.
it is actually XN thing, the latest thing.
Yes, yes,
Do we have
it
any
cannot be
symbol
reduced anymore.
representing it? It's just the definition, or we call it.
It's
Beta NF.
beta NF. Yeah, beta NF.
Wait a second. Wait a second. Beta and F. Equality, and then normal forms and confluence.
Yes.
Uh-huh.
Yes. Yes. So what I was thinking is normal forms is, as I said, it's just the simplest form. There's nothing much about that. And after that, we're going to see the Church Rosser one.
Yeah, yeah.
And also Kai, yeah, Kai, before you came, we were discussing that the book does not do the Church Rosser theorem. So
We mean that
what
it is beta and F, basically.
it is not beta NF. It is
Ah. Mm, mm.
another powerful version of beta NF, let's say.
You
It's
mean
like a nice
MN
prop.
is the more powerful than beta NF?
No, 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 no. Beta NF is the simplest form, but what I'm saying is the Church-Rosser theorem
Ah.
is like a special property about this beta NF.
Okay.
Yeah.
Do you see? Can you see this thing, the blue thing from there? I mean, it is beta NF,
Yes.
not the church.
Yes. It is. It is. It is. It is beta NF. What Church-Rosser theorem says is that if you have beta NF, no, what it says is that if you have a lambda term and it has been reduced to two things, like we did in our example, right? We reduced it to two things. Then there exists a beta NF that is reducible from those two things. So that was the ZV we had. You see? So Church-Rosser says that
you mean basically
say it
we
again.
have beta NF,
Mm-hmm.
and for every lambda term we can I didn't look to the definition, but based from you said.
No, no. So what? Yeah, let me just draw it here.
Okay.
What it means is that if you have a lambda term and you have lambda 1 and lambda 2, so these are like what you get after the reduction, right? So this is one way of reduction. This is another way of reduction. You get this. And what Church-Rosser says is that there must be a beta NF. So this is the special form, which gets reduced by the 2. So see, this was our ZV back then. We had another from the outer side and another from the inner side, and they both got reduced to ZV.
Yeah.
Right?
Yeah.
So Church-Rosser says that this is actually true for every lambda term that has two ways of reducing, or not two, n ways of reducing. Yeah.
Is it true? For example.
Yes. True, because we have the common thing. Yes.
Because in the case with ZV, yeah, we can have. But in the other form, so beta NF is true, for example, for ZV. Okay, right. But we have single
ZV
letter.
Is the beta.
They're not beta equal. Okay. Okay. So we can continue.
Yeah. So that's this is the diamond theorem. It's like a special diamond structure. But yeah, for this little, like it looks simple, but its proof is like very complicated. So what I was saying to Shakhzod before Kai came is that the book does not do the theorem's proof. It just proves a corollary of it. So what I was thinking is that because this is a very important theorem in type theory, we should dedicate a few sessions to just understanding the proof from other sources. What do you think, Kai?
I think that's a good idea, because the thing is, I read about the Church-Rosser theorem, and I mean, it didn't seem like true. It didn't make any sense. Just like I mean, it did make sense after reading the theme, after reading it for 3 or 4 times. But I mean, it's not sticking, or how do you call it?
Yes.
I can't. I mean, if you wake up me at 3 a.m., I cannot tell you, because I mean, I cannot understand it.
Yeah. So but like without Church-Rosser, you cannot actually have type lambda calculus or untyped lambda calculus. You cannot write an evaluator for any language, functional language, without Church-Rosser, because Church-Rosser allows you, it's like, because you're going to have different expressions in a language, right? And those expressions sometimes will have several reductions. Church-Rosser allows you that no matter how many reductions you have, they will always have a simplest form. They can always be simplify it to one thing. So it is very important, especially if you want to implement your own type checker from scratch. This is the kind of thing you need.
Yeah. It's kind of, I mean, after reading it for a while, it seems like related to the thing that I said in the previous meetup. Like if the lambda term is closed, aka a combinator, it can be
Right.
reduced in any way possible, and the outcome is not going to change. It seemed like
Yes.
related.
Yes.
So yeah,
Yes.
it said
Yes.
that after googling for a bit, I found out that it allows us to think in different ways, so we can use different evaluation strategies to kind of.
Yes. So this theorem is important to understand evaluation strategies, or to understand a lot of things, honestly. So we should do a deep dive into it. It'll be good. It'll be difficult, just to tell you. It's so difficult that a graduate text does not include it. So,
Yeah.
it's pretty long, and it's going to be boring. But if we continue, we'll understand something, and it's going to be okay.
Next
Um,
level of abstraction.
Yeah, it is really next level of abstraction. I think if you're able to completely understand Church-Rosser, you'll have a very good grasp of like mathematical proofs, because this one is such a long proof, and if you can keep it in your head, you will be able to understand proofs better. Yeah.
Yeah.
Okay.
Intrigued.
So that's what. Yeah. So that's what we do. We meet next time, and we try to understand Church-Rosser. I have a few resources. I think you have also did some research. Share whatever resource you can. I think we can go with the Berendrecht book, the classic book. I was checking it today. It has a nice proof. There are actually 3, 4 important proofs. The Martin Laws, if you know about him, he's the guy behind the homotopy type theory. He was one of the first people to give a proof, a different proof. So yeah.
From
So I will.
from HOTT, you mean?
Mhm. Yeah,
Homotopy
that the
type
guy.
theory.
Yes,
Hot.
yes,
But
yeah. Hot. Yeah, the guy behind that, Martin Law, he did one of the new proofs for this in the 90s.
Impressive.
Yeah, so we're going to be going that deep into it. I'll share whatever resources I have, some papers, some books, and we'll see what looks good to us. Okay,
All right.
yeah, thank you.
great.
So the classical Berndrecht book is the one, lambda calculus with types, right?
No,
Or the
that's
other one?
lambda calculus. It's syntax and semantics. I will post it
Right.
in the chat.
I found 8 page length paper.
Proof
Maybe
of it? Or
Yes.
it is interesting. Wait a second.
yeah,
I'm sending you. From Martin Love, I guess. I just googled Martin Love Church-Rosser. Yeah.
Yes, that's the paper. No. This is not the Martin Love paper, but yeah, it's another explanation of the proof.
Okay,
Yes,
yeah. It's said that made easy. Yeah, let's see.
yes, but it's not made easy.
Yeah,
that's a trap.
It is a trap.
Sigma
Let
means
me.
any possible. What does mean sigma? Sigma.
Some or what?
But the reduction at sigma is. Oh, better redexes in the and with proper prefix of t. Yeah, it's definitely not easy.
Bro just gave up.
No. I'm observing new
Hmm.
mathematical symbols. There is an arrow upwards, but the left side is empty. It's like one, but it's flipped horizontally. I don't know how to
Yes.
spell this arrow. Half arrow. Subterm of
Alright.
E rooted at sigma. Ah. Uh-huh. Wait a minute. I mean this symbol, and I think yeah. Subterm of
Oh,
E
that's
rooted at sigma.
yeah. Yeah, that's the subterm.
Uh-huh.
It's notation. You'll get used to it pretty quick. It's notation. Yeah,
Okay.
it's just like the syntax of a language. We don't worry too much about the syntax.
Yeah, people joke at mathematical syntax that it's worse than JavaScript.
Yeah, so I have sent the original paper by Church and Rosser. There's the Berendrecht book, the classic book.
20
Yeah,
megabytes.
what else?
Ah, it's just
It's a
scanned.
700-page book. Yeah.
Ah, uh-huh. The book which we'll review the next session. Study
Yeah,
from.
so we'll go through like 10 pages or maybe, yeah, 8 to 10 pages of that book. Yeah. Yes. So yeah, we'll see a couple of proofs and we'll see how they're a bit different, what they do better. And yeah, I assure you, once you understand Church-Rosser, you'll have a better idea about type theory. It's really fundamental. Yeah.
Thanks to you, I now understand mathematical for loop.
Okay. So we meet when? When is a good time to meet?
Actually, we will be outside of the city next weekend.
Okay.
We can actually do the next session if you're comfortable next week during regular weekday, not
Yeah,
the weekend.
regular weekdays is yeah, weekdays is fine except Friday and Wednesday. Yeah, except Friday and Wednesday, I'm fine.
Okay.
Alright. Next Thursday it is then.
Yeah,
Thursday.
next Thursday is cool.
Okay, that's fine.
8th August.
8th August. That's
Yeah,
fine.
8th of August. Yeah, yeah, yeah. So another thing that I was wondering is because we will be getting into Church-Rosser like pretty deep. I was wondering the rest of the stuff that's left in the chapter, which is like just one section about um,
Y
I
Combinator.
yeah, the fixed point theorem. The fixed point theorem. It's
Uh, Fixed
yeah.
pointed
So what
theorem.
is 1.10? So what I was thinking is um, should we do it after church roser if it's cool with y'all? Or well, to me, it's not too much. Honestly, it's a just one theorem, which is simple. But
We
it's
can
up
do
to
it
you
to
guys.
warm up, or
Yes.
and then deep dive into that church roster. That's I
Okay.
think that's
So
going to go. Yeah.
okay. So next meeting we do some time with fixed point theorem, and then we get into church roser.
All right. So we're going to be proving that in paper or lean or calc.
We should do first paper, really. We cannot do lean unless we understand it in paper.
Fair enough.
Yeah.
Right.
Yeah, we can make it a kind of side project because does there, I think there must exist one in Cork. I don't know if there is in Lean. It, probably someone has also done it Lean. But we can have it as a side project as once we understand it in paper, in natural language, we can then have it done in Lean together.
All right.
Yeah, that will be an achievement. Yeah, honestly, if we can do church roster in Lean, that's an achievement. Okay. So next Thursday it is same time, 2 p.m. UTC. Sorry, is it 7 p.m. GMT plus 5, right?
Yeah, yeah. Or GMT
Okay.
3 by GMT 1 0, yeah?
Yeah,
Is
2 by GMT 0. Yeah.
2 by yeah, right.
Okay. Okay. So that's it. We're going to do this fixed point Y Combinator and then church roster. Cool.
All right.
Okay, guys, thank you for your time. This was good. Yeah,
Yeah, thank you too
Thank
very
you
much.
too.
no worries. Okay, have a good evening. I shall meet you next Thursday.
Yeah, same
night.
for you. Good night.
See you. Good night.
Ingliz tilida словарный запасым tugab qoldi to'g'risi.
Bugun yaxshi bo'ldi lekin.
Yaxshi bo'ldi, to'g'ri. Просто nima deyishni o'ylab o'tiribman-da, qanaqa tushuntirsam ekan deb, qanaqa desam ekan deb o'ylab o'tiribman-da. O'zingiz qanday bo'ldingiz?
Yo, menga yaxshi bo'ldi. Men o'zi kitobda o'qiganim, tushunmagan joylarim, как раз tushunmagan joylarimda qo'shilibman-da.
Da,
Chapga, o'ngga redaction o'shani sal-pal kallaga kirmagandi. Как раз o'sha joydan qo'shildim.
menga sal
O'sha
tushunarli
sal
bo'ldi.
oldiroqda.
Qayerga ketib qoldim? Bu mana saqlab qo'yaman o'zim bo'lmasa. Stop.
Yomon ham qotish boshladi ekan, lekin Excalibur chizib o'tiribsiz. Menda ko'rinmayapti, streamga qarab o'tiribman. Sal-pal delay bo'lsa ham ko'rinishi uchun.
Da shunaqa nimadir qoni og'rib qoldi. To'g'risi menga mana bunaqa narsa yo'qoldi-da. То есть men kallamda agar mana bunaqa narsa qilib tushunsam, siqilib shunaqa formada.
Qani bir-biriga relationship nima?
Relationship. Ya, в принципе, tushunarli bo'ldi. Menga eng yoqqan tomoni mana proof'i yozilishi.
Qoldi.
Menga juda yoqdi to'g'risi. Ozgina men bu sintaksisga o'rganishim kerak. Men bu all borku chapacha. Men bu sintaksisga mana sintaksisga. For all I which are from 0 to n, inclusive, exclusive qanaqa qilishni o'ylashim kerak. We have x0 battar. Noldan. Короче, for loop mana bu for loop. Tupo for loop. Qo'pol qilib aytganda.
Shunaqa? Ya'ni universal kvantifikator. Har bittasi uchun degani.
Da, men inductionni ham tushundim. Proof by induction. Ya'ni bizda ikkita narsa bor. Mana. Bizda mana bu bor. bu bor. Biz proof qilishimiz kerak. Ikkovini qo'shsa anavi bo'ladi. Ya'ni aynan mana bu qismini ulab qo'ysak bo'ldi ekan, to'g'rimi? Mana bu qismcha.
Shunaqaroq, ishqilib har bittasini case by case qilinadi.
Ya'ni biz L dan N ga o'ta olmaymiz, chunki mana bu beta reduction singular operatori. Bittalik. Mana bu narsaga sal struggle bo'ldim-ku, keyin tushundim lekin. Mana bu relation qani edi? Mana bu narsa. Ya'ni definitionda yozilgan yo u tomonga yo bu tomonga bo'lsa deb qayerda edi? Mana. Either mana bu qismi. Men prosta o'ylagandimki nima, agar yarimta bo'lsa, ya'ni biz mana bu beta equivalence chainni o'zini emas, natijani aynan link qilar ekanda, pointer natijaga link bo'lar ekan. Ammo o'ylabmanki, mana bu directionda qaysi tomonga qarashi, bu aynan mana bu aytadi-ku, destination bor, journey bor. Journeyga qaramasdan destinationda o'zini aniq qilish kerak. Aylanib o'tib kelishi mumkin, primoy borishi mumkin. Destination. Buni tushundim, buni plus minus.
Church roster tushunsa, shu bilan keyin untypedan pishadi, simple type'larni takror qilsam yarim ham pishadi inshaalloh.
Men biroz simply type'ni ozgina o'qidim, boshini. Prinsipi yomon emas, to'g'risi. Prosta biz ikkinchi narsani aniqlayapmiz, introduce qilyapmiz. Prosta type'dan o'qilamiz. Notation buni m, masalan, qaysidir type. Hozir ko'rayda. Ismlashib ketdi уже.
Sodda tiplar bo'ladi.
Sodda tiplar bo'ladi, lekin dalishi hali aniq emas. Ana nima edi? Voy o'tib ketdim. Kitobdan hozir stop qo'yadi. Ana gammamiz bor edi-ku.
Kontekst.
Nima deyiladi? Hozir men topaman. Topib tashlayveraman.
Kontekst.
Adashmasam simply type ichida turardi. Yo'q, mana bu narsa. Mana bu narsamida, qarang. Shumida bizning o'yimiz hill naminglarda
Inference rules deyiladi. Shunaqa. Oltitasi bor unda. Bunda 3 ta simple type.
Qaysi bitta edi? Adashmasam shu kitobdamidi? Kursda adashmasam lambda conf paytda birinchisi lambda confmidi? Meeting bo'lgandan oldin, confdan oldingi kutubxonada. Ili qizil kitobdamidi?
U yo'q, unda emas edi. U Aleksandr Chichigini tolqi deydi u. Unda lekin bitta emas edi. Bitta-bittalab ko'rsatganda unda.
Tak, qarang, ismda bor, mana bu kubimiz bor. Ya'ni mana bu kubimiz borda.
Ha.
Kubimiz bor edi. Ya'ni eng prostoydan boshlab keyin mana yerda strelkalarimiz bor edi. Keyin oxirida ana edi. Big Boss. Mana bunaqa edi strelkasi, adashmasam. Shunaqamidi, to'g'rimi?
Shunaqa. Pastdagi eng chapdan, tepadagi
Da, mana shunaqaroq qilib ketardi. Mana bunda hamma xususiyatlari bor edi. Xuddi qo'pol qilib aytganda interfeysma trade'larga o'xshagan narsa-da. Mana bu bitta xususiyati, xuddi mana bu monod yo'g'i applikativda
morfizm.
Anosi mapping bo'lish degan bor edi, to'g'rimi? Applikativdamidi, monoddamidi? Morfizm bo'lishi.
Morfizmi liboyda. Bo'lsa morfizmda adam bo'lgan. Ishqilib, mana shunday featurlar qo'shilib ketaveradi. Shuni endi bu kitobda
Da. Uzr. Men bu narsani bittasi ko'rdim-da. Hozir sizga tashlayman. Kim tashuvdi? Qayerdadir ko'rdim men hozir. Az. Mana bu narsa.
Так. What part of konferensiyaga kiyib olish kerak shuni.
Qayerda
Part of
qayerdadir
Hindli
ko'rdim, to'g'risi. Kimnidir futbolkasida ko'rdim. Hindli millarda HM deyiladi, to'g'rimi?
Hindli Damas minlari ham bo'ladi.
Ya'ni mana bu kontekst, kontekst bo'ladi.
Hamma
Bunga-
tiplar o'sha yerda turadi, ha.
Bunga yetib
Qaysi
kelamiz-ku,
terimni
to'g'rimi?
nima tipi bor?
Bu kitobda ichida yetib kelsak kerak, adashmasam bunga. Adashmasam o'sha.
Hindli minlargami?
Yo'q,
Ha,
endi nima emas,
Hind-
umuman mana bu
kelamiz.
notationni tushunish uchun.
Ha,
Notation uchun.
bunga yetib kelamiz. Уже andan boshlanadi, сразу simple type'larni kalkulsiyadan. Уже deduction qilish boshlaymiz edi, logический bo'lgandan keyin.
STLC.
Ya'ni nima demoqchi edim? Gamma kontekst bo'ladi. Kontekst ichida qaysi termin nima tipi bo'ladi? O'sha hindli minlar o'zi tagida system f omega. Ya'ni hindli minlar уже type inference da bu. Biz уже type theory'ni pure o'zini o'rganamiz. Menimcha buni ham aniq bilmadim, lekin hindli minlar ishqilib hindli minlar lekin mana shu system f system f omega ga teng. System f omega deyiladi. System f deyiladi aniqrog'i. Bunga yetib boramiz. Undan ham oshib ketamiz. Hali lambda d ga boramiz biz. Lambda d ga borib, dependentlardan
Kitob oxirida.
tushadi.
Qizil kitobimizchi unda nima edi?
Anima Pierce'ga
Da,
tuple.
tuple.
Unda ko'proq praktik narsalar yozgan. Ya'ni OCamlda har bitta u dasturlash tillariga yaqinroq. Hozir чисто matematik tarafdan o'rganamiz-da bularni.
Da, mana lambda
dasturlash tillariga qanaqa ishlatish kerak. O'shani mayda-chuydadan boshlaydi, u ham zo'r o'rgatgan. Uni qayoqqacha borishini bilmadim, lekin ishqilib u ham uni ikki xili bor. Tuple bor, keyin at-tuple bor. At-tuple degani advanced topics in type tuple o'zi
to'g'ri, kitobda yarim
Mayda.
lambda deymi? Kitobda yarim lambda deya ekan-ku, 211 betdan boshlanib.
yo'q.
Ha.
Yo'q. Murakkabda juda ham. Chunki dependent type'larga o'tgandan keyin bitta syurpriz bo'ladi. U syurpriz nimadan iborat? Tiplar bilan termlar farqi qolmaydi, chunki termlar tepaga chiqsa, type'lar atrofiga ham chiqa olaveradi, type'lar pastga ham tushaveradi.
Qiziq,
Undan
bizda
keyin-
shunaqa til bormi? Expression ichida type levelga o'tib, chunki ko'p tillarda type levelda
Bor.
expressiondan olib.
Ya'ni misol uchun qanaqa narsalar qilib turasizda, yoniga prooflar yozib ketaverasiz type levelda. Ya'ni o'shani keyin funksiyaga argument qilib beraverasiz keyin. Unda ham headni ko'rsatadimi? Bitta head list oladi, list term levelda. Keyin ikkinchisiga proof oladi, ana h bordi, hypothesis.
Bitta zo'r narsa
katta
aytaymi?
bo'lsa headini olish.
Bitta zo'r narsa aytaymi? Rustda type leveldan turib term levelni aksesini qurmaganman lekin. TypeScriptda bor lekin.
Yo'q, iloji yo'q. TypeScriptda ham iloji yo'q. Qanaqasiga iloji bor?
Type leveldan key of type of qilib expressiondan qo'pol qilib aytganda,
Ya'ni misol uchun type olib turib term qaytara olmaysiz-ku? Bo'ladimi? Bo'lmaydi uni.
yo'q, type of qilib termni typega o'girasiz.
Termni type'ga o'girsa bo'ladi, ha.
Vot,
Termni
Rustda
misol uchun type level string,
bilmayman
type
shuni.
level-
Shuni imkoni bormidi? Rustda.
Bor, Rustda bor. Termlarni type'ga chiqarsa bo'ladi. Rustda bitta prikol joyi type sistemasi Turing complete, ya'ni type sistemasi dasturga yozsa bo'ladi. Turing complete hisoblanadi.
Gotcha. Demak, значит, unchalik davrda, uncha darajada kirmabman ekan ichiga. Просто men uchun nima type leveldan term levelga access, bu type of, key of, mana shunaqa narsalar aynan termga qarab type'ini olib, nimadir qilish. Qolgani уже type operatics. Uni type akrobatika deyman-ku. O'sha narsa.
Lekin tiplardan turib termga tushish ekan juda ham o'shunchalar misol uchun boshida misol uchun prikolniy ko'rinadi. Ya'ni Dunning-Kruger effekti bor-ku. Hech narsani bilmasa og'zi ko'p ishlaydi, ko'p narsani bilgandan keyin og'zi yopilishni boshlaydi.
Shunday.
Guruhlarda ham sezib o'tiramanda, ya'ni misol uchun Vlad amaki bor-ku, Vladislav Zavyanov, Intindex.
Hop.
O'shanga savol berishganda so'raydi, type deganda nimani tushunasan deb boshlaydi-da. Chunki dpn typelash ustida ishlaydi-yu. Dpn typelab bo'lgandan keyin typelar bilan terminal farqi qolmay qoladi. Misol uchun Любой hozir beginner TypeScript'ga yetsangiz type'la nima siz valaq-vulaq gapirishni boshlayveradi, lekin bundoq sal o'rganishni boshlagandan keyin terminal bilan type'la farqi qolmay qolar ekan.
Bitta narsada qarang, agar biz hozir common Lisp yoki Lisp olsak, unda biz qaysi leveldagi kubdamiz? Kubba qaysi tomondamiz? Adashmasam, imkon boricha
Hech qaysi emas.
untypedga yaqinroq emasmizmi? Masalan, Lispda. Plus minus.
Lispdami?
Lispda type'lar bormidi? Hozir chota eslolmayapman.
Dynamic type'lar. Common Lispda type'lar yo'q, короче. Type'lar Lispga qarshi yuradi. Ya'ni Lisp hamma dinamik, kodni olasiz, evaluate qilmagan kodni beraverasiz, code is data.
Ya'ni
Type'li
hozir
Lisp yo'q.
biz o'rganadigan untyped men bilganimda kalkulusga eng yaqini shu-da, Lisp.
Shunaqa tushunsa bo'ladi.
Tipo shunaqa tushunish ana qilsak, comparison qilsak, tier list deylik. Tier list emas, roadmap qilsak.
Listdan ba'zilari check qiladiganlari bor, SBCL balobatlar, lekin nima deydi? Lisp seriyoz narsa emas, короче.
Okay. Mayli, men to'g'risi ana notebookim o'lib qoldi-da ertalab.
Kanalga post qilingan ekan, reviving MacBook.
Foydasi bermadi. То есть hardware levelda ekrani ketdi, to'g'risi. Siqilib o'tiribman.
Tuzatsa bo'lsa kerak, yo Apple tuzatish qiyinmi?
Endi imkoni bo'lar, quramiz. Srazu boshqasini o'raveraman. Imkon boricha Apple emas, oddiy.
Batib ma'lum aytasiz kommentda.
Apple'da zo'r tomoni nima edi? Batareyada. Bo'ldi. Shu joyda tugadi. Zo'r narsasi. Chiqib. Mayli, masalan, notebooklarni ozgina research qilay. Sizga omad, rahmat kelganingiz uchun. Yeslicha yana o'tiramiz. Sekin tepishni boshladi, to'g'risi.
Men ham o'zi boshda qo'shilganimda уже mandan oshib ketgandek tuyulib ketdingiz-da. Sekin men ham tepish boshladi keyin. Keyin tushunib yetdim.
Mayli, charchamang. Real yarim kutublamda o'rganamiz. Dependent type'lar, to'g'rimi?
Dependent type'lar.
Bundan ham superiori bormi? Yo, hali humankind o'ylab topmadimmi deylik.
Dependent type'lar har xil turlari bor. Refined type deganlari, refinement type, ya'ni misol uchun array anda ko'rsatdimi? Array nechinchidir elementida qiymat borligi. Misol uchun TypeScript'da bor, if bilan tekshirsangiz, undefined qaytarmasligini tip
Qarang, men sizga zo'r narsa ko'rsataman-da, mana type theory'ni real life'da. Masalan, sog'lom odam bor. U boshida sigara chekishni boshlaydi. Keyin bu yoqqa pivo qo'shiladi. Keyin o'g'ri qanaqadir vodka bo'ladi. Keyin qo'shiladi bir-biriga. Ana bo'ladi. Nima edi? Kubimizga o'xshagan narsada, kubimizda masalan har xil tomonda har nima turadi. Keyin bizda ana bor. Nima edi? Math bor deylik. Math'da ham oddiy math bor. Keyin ko'kimda ana
96.
Heisenberg qilgani bor. 96% mana. 98% edi. Qanaqadir deydi. Heisenberg qilgan math bor. Biz chiqilib shunday ketiladi, ha?
99.1 ekan. Gap yo'q, voy gap yo'q. Biz ham shunaqa kuchlisidan ketamiz.
Ya bizda hali endi
Nima?
baby math.
Ha. Shu dependent type'dan kuchlirog'i dependent type'dan o'zi ham turi bor, ya'ni misol uchun lindagi dependent type'lar bilan kokdagi dependent type'lar misol uchun farqi bor. Logika sistemasiga ham qaraydi, ya'ni misol uchun Haskell'da logika sistemani вообще yo'q desa ham bo'ladi, chunki false proof qilsa bo'ladi. Agdadagi logichni sistema farqi bor. Hali chunki type theory ham logikani bir qismi-yu. O'shanga ham qaraydi hali. Logika kuchaygan sari bu ham kuchayib boraveradi. Calculus of inductive construction deydi-yu, COC. Linda o'shada CIC. Dependent type'lar ham o'zi ham nima desam bo'ladi? General narsada, ya'ni dependent type degan narsa o'zi yo'q. Ya'ni dependent type turlari bor. Refinement type bor. Yana nimalar bor? Self type balobatda narsalar bor. Ya'ni bu dependent type degani bularni klassifikatsiya nomida. Rustam, dependent type'larning turlari rosa ko'p.
Samagon. Ha, craftoviy, dependent type deylik. Craftoviy pivolar bor, hammasi har xil. Kimdir kirsa.
Type theory nima bo'lyapti degani.
Ha. Ya, men qachondir tushunishni boshlayman. Qachon men buni tushunishni boshladim. Men bu kontekstni tushunishni boshlayman, men bu simvolni tushunishni boshlayman. Free deganim o'zimizdan o'ylam
Ozod xat.
ozod qilmi bu? Okay,
Qaysi free ni aytadi?
qarz kiramiz. Men bu freega. Men o'yladimki, lambda kalkulusdagi free. Ya'ni bush kontekst. Ya'ni bush emas. Kontekstga bush variable emas degandek gapda, xuddi o'sha o'rganganimiz. Men bu g'alatani
Gen
bilaman.
bu generate gen rule mancha generate bir bo'laydi, ya'ni gammani ichida bo'lmasligi kerak.
Ha, mana qarang. Tushunishga harakat qilamiz, kitobsiz. Endi men kitobsiz. Bu untypedagi 3 ta qismimiz. Ya'ni variable, application, ya'ni bitta narsani chaqirish, bo'lganda, и abstraksiya.
Va abstractionni type checking rulelari.
Endi qarang. Men bu yoqda agar x variable nomi sigma, men bu kichkina sigmacha type.
Kichkina sigma type shunaqa.
Kiradi hamma type'lar ichiga, to'g'rimi? Gamma degan, kontekstimiz.
Yo'q, kontekstning ichida degani abi, ichida.
Kontekst ichida. Men bu nima degani? Men bu tayoqcha.
Implies. Ya'ni bildiradi degan ma'nodan implication deb tushunsa ham bo'ladi, uni adashmasam.
Ya'ni men bu kontekst ichida
follows deganida, ya'ni gamma bo'lsa, demak x uni ichida, ya'ni gamma bo'lsa degani x termni sigma type bo'ladi degani. Implicationga o'xshagan narsa.
Men bu tay adashmasam.
Tau.
Tau, men bu tcha bor-ku.
Endi application, ya'ni bu juda ham sodda. Ya'ni aytayaptiki, bizda e0 degan funksiya bor. e0 tipi tau oladi, tau prime qaytarib beradi dotda. Va gammani ichida yana bitta bor dotda, e1 dotda uni tipi tau dotda. Ya'ni e0 ga tauni bersak, tau prime olamiz dotda. Ya'ni application qilib tauni berib tau prime olamiz degani. Ya'ni application, ya'ni argument oldi, return type'ini infer qilamiz ish qilib.
Da. Abstraksiya ichida variable'lar bor. Balo. X men bu abstraction of x over e. E deganda men return value deb tushunsak bo'ladi.
Yo'q, deganda pointer apida.
Uni
И
tipi
to'g'ri, return value.
type kiruvchi,
olib.
tau prime
Mhm.
anaqa qildida. Let bu declarationmi shunda? Da declaration ekan.
Bu let shunaqa let expression, ya'ni bu hozir adashmasam polymorphic let expression adashmasam.
Instagramchi.
Ya'ni Instagram instantiate adashmasam.
Instantiate.
Bu
Aha.
mana biz 4 burchak simvoli bo'lgan. Mana faqatgina 4 ta rulni yodlab qo'yaman. Misol uchun soat 3 ta uyg'otib tursangiz ham aytib bera oladigan darajada yodlaganman 4 tasini. Mana bu ikkita oxirgisini bilmayman.
What part of it don't understand? Ha. Bizga aytaymi? Yozibdan sen aytaman. Men yaqinda anavi qilishni boshladimda. 6 aprel bo'lsa, hozir avgust 4 oy o'tdi.
Ha.
4 oydan
Birinchi
burun
marta
functional programming qilyapman.
Ha. Berilib ketsa-chi.
Ya'ni men hozir ozgina mayitlarga keldim. Pivo ichib o'tiribman. Kitobni tugatsak vodka level bo'ladi. Men level bo'ladi o'ylayman, bilmayman yana ham. Keyin yog'i ochiq bozor. Qaysi yoqsa?
Logikani xod balobattarlar.
Bu
Xodda ham ikki xili bor.
mana bu o'lishimdan oldin. 90 yosh bo'lgan paytim mana shu levelga keldim. Hali perfection bor. U vaqtgacha kimdir men bu ChatGPT mana bunaqa yana bitta branch o'ylab topadi. Cloudy buni o'ylab topadi. Lamas buni o'ylab topadi.
Lekin menimcha ancha-muncha oson bo'lib ketadi mana shu basiclarini sal-pal kalla tushib olsa, keyin logika o'rganishni ham boshlasa, keyin
Anon akaniki yoqadi hozir. Oti nima edi? YouTube'da category theory
programmersmi?
theory.
Bartosh Milevskiy.
Yo. Ana bor edi-ku. Oliver Lugmas.
Ha, ani tashlagandingiz.
3 xil anon kursda oz. Oti nima edi? Immagur category theory for beginners, adashmasam. Richard Southwell. Shu edi adashmasam. Da, Richard Southwell. Va u ko'rsatardiki, playlistlarning ichida bor edi category theory for beginners. Yo, emas. Boshqachasi bor edi. Topology. Yo'q, men ko'rganim. Homotopy type theory. Yo, u spetsialniy playlisti bor edi, biratda. Modern foundations of bo'ldi. Esladim.
Okay, so we're gonna
Esladim. Hozir men uni tashlayman. Mana. Mana. Piramidasi bor edi, biratda. Tushuntirganda. Biz ko'rindi-ya? Ya'ni bu kategoriya teoriyadan nimadir tushuntirishni boshlardi va xuddi shu narsani logika orqali describe qilardi. Va xuddi shu narsani type theory orqali describe qilardi. Ya'ni uchovi bir-biri bilan shunday bog'langan chambarchas deydi-ku. Треугольникcha.
Shunaqa.
Shunga yetib kelamiz. Mazza.
Chunki logikani o'zi ham bir juda ham qiziq narsa ekan. Hammasi bir-birini kompliment qilsa, menimcha yorug'lik tezligida vashni o'rganib tashlasa kerak. Shu boshida bir qiynalib olib yaxshigina.
Tak, men hamma notlarni shuni просто сохранить.
Localga JSON saqlanib qo'ysa bo'ladi, adashmasam.
Shunaqa qilamiz. Endi men bilan qoldiramiz uymi? Spirit 99%. Turaversan, hech qisi yo'q. Export image embed skin bor. Meeting type theory meeting 01
Uchinchi shekilli bu.
08 2024 deb yozaman. Bu safarmi? Yo'q, uchinchisi emas. Bu ancha 4-simi adashmasam.
Ha, uchinchisi yo'q.
Hozir ko'ramiz. Okey.
1, 2
17 megabayt ekan. Tak, buni yopaman.
rasmimizni.
Tak, mana buni ishga tashlayman. I don't think there is at least multiple proofs of charter formats in Cockney for this will be significant contribution of in either them.
Akras.
It's going to be
Ham biza o'rganib olamiz, ham
humongous task.
contribute.
It will benefit both for learning time mathematical bomba.
Contribution qilib yana gap yo'q.
Tak. Excalibur drawings export is some extra the only mechanized proof I found using Boyer-Moore theorem prover Shankar. Quite astonishing that such an important didn't get formalized. I'll ask in the communities of Lin and Koch to ensure if there is something that already exists and I didn't find. That's cool. Qanday ochsa bo'lar ekan buni? Show in folder.
Rasm ochmayaptimi sizda ham kattaligidan?
Chrome'da ochdi. Bu protsess nimaga katta? Chunki anavda eksporti ham bor. Ya'ni bu xuddi shu narsani Excalibur'ga import qilsangiz ishlaydi.
Ha. Anunda fehda ochdim anda.
Da. Men bu narsani mana qilib open qilib downloads ichida mana bu narsani shuni import qilsak hamma mayda-chuydalargacha import qiladi. Yes. Cool. Mayli, shu joyda sekin to'xtatamiz. Chatdagi assalomu alaykum hammaga. Bu nima va nima uchun ishlatiladi degan narsa, bu dasturlash tillaridagi tiplarni o'zimni qanaqa tushuntirsa bo'ladi. Computationda Короче, dasturlashda eng nazariy tomonlari, matematikaga yaqin tomoni desak bo'ladi, to'g'rimi? Bizda bor masalan qanday anaqa narsa bor edi-ku. Bizda bor
Type
yo'q, 0101 bor. ISM bor. Ya'ni binary bor.
Lamda kalkulus shu 0101 darajada low level.
Sal abstraktroq u narsasi ISM, assembly. Baribir binaryga yaqin, lekin anavi, mana bu sal gap bor o'rtasida. Keyin keladi bizda C. Bu ISM, ya'ni mana bu dunyoga compile bo'ladi. To'g'rimi? Ya'ni mana bunaqa imaginary anavimiz bor, abstractionimiz bor. Compiler tillar, bilmayman, C++, bolabattar, superset bolabattari, mayta rust bor deylik yana yangilarda. Keyin yana bitta abstraksiya bor. Endi bu tomondan o'zi ko'payib ketadi abstraksiyalar. Mana bunaqa tushunsak bo'ladiki, bizda mana bunaqa yana bitta abstraksiya bor. Bu interpretatsiya qilingan tillar. Interpret. Masalan, JS, PHP deylik. Bu narsa mana bu narsada execute bo'ladi, lekin o'rtada qanaqadir yana qaysidir stepi bor. Qo'pol qilib aytganda. Ishqilib
Mhm.
Shunaqa narsa bor. Va yana bitta bunda alternativ funksional dasturlashtiruvlari deylik. Hozir endi bu 2Dga chizib bo'lmaydi, faqat 3D, 4D qilish kerak. Relationlari ko'p.
To'rda bo'lib ketdi.
Haskell bor deylik. Bu baribir kompilatsiya qilinadi ISMga. Lekin agar fikrlash narsamiz mana bunda boshqacha bo'lsa, qo'pol qilib aytganda mana bunda boshqacha deylik. Bitta imperativ fikrlash deylik. Bu уже funksional fikrlash bo'lyapti. Mana bu tomon. Endi nima bo'lyapti? Mana bu dunyo bizda qo'pol qilib aytganda Turing anosidan kelgan, to'g'rimi?
Monopoliya hozircha biladi.
Turing deb aytaylik. Bu lambda kalkulus deylik. Qo'pol qilib aytganda. Lambda deylik, kalk. Ya'ni shogird ustozdan o'tib ketdi degandek gap. Bu Alonzo Church bo'lsa, Alan Turing Alonzo Churchni anosida brachkasi bo'lgan. Biz o'rganadigan narsa ikkita computationni anosi matematikani, to'g'rimi? Aytda matematika dunyosi bo'lsa, kattasi Big Brotherni matematikaning territoriyasida bo'lsa, computation teoriyasi. Hisoblash ya'ni. Ya'ni bu ham hisoblash, bu ham hisoblash. Endi yana bitta 4da, 5da dedim-ku, mana bu yerda o'rtasida chiziq bor. Mana bu yerda nazariya bor. И pastida уже amaliy bor-da, qo'pol qilib aytganda. Ya'ni biz ishlatadiganimiz, biz hayotiy kundalik vaqtimiz mana bu joycha, mana bu qismchasi. Ya'ni bu ham emas даже. Biz mana bu qismda ishlaymiz. Yoki ko'proq mana bunaqa qilsak ham bo'ladi. Mana bunaqa avvalniroq. Давайте mana bunaqa qilaylik. Mana bunaqaroq ishlaymiz, qo'pol qilib aytganda. Mana bu chiziqda tipasi anavi teoriya, pasi praktik. Qo'pol qilib aytganda. Ya'ni даже mana bunaqa qilsam ham bo'ladi. To'g'rimi? Ko'proq nazariy tomonlama o'ylaniladi Haskell funksional tilida. Endi bilmadim, buni qalay chizish kerak. Plus minus shunaqa deylik. Mana bular ikki xil maktab desak bo'ladi. Maktablar. Ikki xil yondashuv. Umumiy narsa bir xil, mana computation matematika degan.
Kelasi equivalent. Kuch jihatdan.
Ya'ni ikkovi bir-biriga shunaqa. Kuchi bir. Endi qaysi birini o'rganyapmiz? Biz prinsipiy mana bu narsani o'rganyapmiz. Qora qanaqa rangim tugab qoldi to'g'risi. Biz mana bu narsani o'rganyapmiz sekin-sekin. Ya'ni hozir mana bu narsani ham xato qildim-da, hozir mana qilaylik. Agar mana bu tomon tepasi nazariya pasani bo'ladigan bo'lsa, biz hozir как раз taки o'rganyapmiz aynan mana bu qismni. Qo'pol qilib aytganda mana shu qismni o'rganyapmiz. Lekin
va qo'shimchasiga
bu hozir 6-dimension bo'lyapti. Bizda nima bor?
Zo'riz lekin shunaqa narsani qanaqadir vizualizatsiya qilsa front-endda ham
ko'rish kerak. Men shu tomondan o'ylayman. Ko'proq nima uchun o'rganyapman, vizuallashtirishga harakat qilyapman. Ertaga boshqa JavaScriptchilar uchun tushuntirish uchun osonlikcha tushuntirsa bo'ladi, mana bu chuqur kirib ketmasdan. Ya'ni tasavvur qilishga konsepsiya. Bizda endi mana bunaqa narsa bor. Funksiyalar bor. Mana yerda keyin TypeScript qo'shilib keldi, tiqilib keldi. Biz birinchi mana bularni o'rganib olamiz. Keyin bunga o'tamiz. Ya'ni kitob bo'yicha yana nima desam buni, dasturlash tilini olsak, qanaqadir dasturlash tilini olsak, boshida biz o'rganamiz, uni hisob-kitob qilish qanaqa ishlaydi. Keyin o'rganamiz, tiplar qanaqa quriladi, keyin nimadir quriladi deb mana bunaqa qo'shib ketaveradi. Ishqilib. Nazariya jihatidan. Siz o'ylab turing nima, shunday o'zi tubimizga kirib chiqing. Bas.
Bu yoqda lambda calculus bo'ladi, bu yoqda Turing machine bo'ladi. Ishqilib, essentially ikkalasi bir-biriga kuch jihatdan teng. Hammasi bitta vazifani bajaradi, faqatgina boshqa yo'llar bilan. Tak. Bu yoqda computation deymiz, keyin hozir. Streamda qayerda? Tak ko'rinadi ekan. Bu yerda computation bo'ladi. Hammasi borib computationga borib taqaladi baribir. Tak. Yaratuvchimiz hammasi computation bitta narsani hisob-kitob qilyapti. Turing machine lambda calculus ham Turing machinega asoslangan mana shu nimalar bor. 010101li tape bo'ladi Turing machine'ni. Hammamiz biladigan lambda calculus desa, bunga ekvivalent bo'ladigan nima bo'ladi? Lambdalar bo'ladi. Lambda termlar bo'ladi. Ya'ni funksiyalar shunchalik low levelda. Ya'ni bular bilan ekspress qilinadigan narsalarni biz lambda bilan ekspress qilamiz. Raqamlardan tortib funksiyalargacha hamma narsani lambdalarda. Keyin misol uchun buni ustiga rostdan 3D 4D 5 deb bo'lib ketar ekan. Bu yerda misol uchun ustida assembly bo'ladigan bo'lsa, bunga assembly kerak emas. Chunki nima desam bo'ladi? Lambda juda ham high level tuyulishi ham mumkin, lekin juda ham low level o'zi narsa. Chunki unda hamma narsani foundation o'zi Alonzo Church bu narsani matematikaga asos bo'lish uchun o'ylab topgan. Butun matematikaga asos bo'lish uchun, lekin butun matematikaga asos bo'ladigan darajada konsistent emas edi. Ishqilib, lambda calculus bu yerda shu bo'yayotganingizdek 3D 4D bo'lib ketadi o'tdim.
Da.
Chunki Haskell ham borib assemblyga chunki borib Haskell baribir ham o'zini lambda calculusga compile bo'ladi, lambda calculus keyin borib turib assemblyga compile bo'ladi. Hozirgi vaziyatimizda, chunki Turing machine hozir monopoliya bunda, lambda calculus bo'yicha mashinalar umuman yo'q. Endi shunaqa amalab turiladi. Misol uchun Haskell o'zi shunaqa kompilatsiya bo'ladi. Endi bularni kompilatsiya qilishga kompilatsiya qilamiz, run qilishga run qilamiz, lekin type theory'ni bizga kerak bo'lgan jihat qayerda? Type theory o'sha tuple'da yozilgan, types and programming language boya qizil kitob bor edi-yu. Unda boshida aytib o'tib ketadiki, Pierce type'lar formal verifikatsiyani kichik turi deb ketadi. Unda o'ylab qarasangiz, shundan keyin kallamga tepib qo'ygan. Rostdan ham deb qo'yganman-da, ya'ni biza tiplar bilan invalid programmalarni exclude qilyapmiz. Ya'ni unaqa programmalarni compile time'da kech qilyapmiz. Type theory shunga kerak bo'ladi. Xo'p, o'shalarni tiplar qanchalik kuchli bo'ladigan bo'lsa, shunchalik darajada ko'p buglarni ushlab olishimiz mumkin. Misol uchun, nega JavaScriptda backend yoziladi, samolyotlarga JavaScript ishlatilmaydi? Chunki oddiy odamga uncha narsa kerak bo'lmaydi. Lekin, misol uchun Boeing yoki qanaqadir boshqa kompaniyalarda ko'p narsasi kod bilan proof qilingan bo'ladi-da. Misol uchun NASA Lean ishlatadi ba'zi joylarda. Misol uchun kosmosga C++ da narsalar yozgan bo'lsa ham, u narsani anchagina mana shunaqa narsa orqali tekshirgan bo'ladi. Ya'ni bu narsa statik analizga tushunsa ham bo'ladi. Programmani run qilmasdan to'g'riligini isbotlash. Chunki run qilganda xato chiqib qoladigan bo'lsa, juda ham katastrofaga olib kelishi mumkin.
Tak, mana yerda bitta narsa qo'shmoqchiman. Qarang, mana bu narsani alohida emas, mana bu chegarasiga 2 marta bosib, mana bu ramkani ichiga yozsangiz bo'ladi.
Aha. Ha,
Tak.
ichiga yopishib turadi ekan shunday.
Aha, o'zi anavi bo'ladi. Tak. Mana buni qora qilaman. Всё, нормально. Ya'ni ish qilib anavi bo'ladi. Aytmoqchi bo'lganim, ichida yana mana yerda matematika deylik, chunki baribir mana Alonso amaki ham matematika uchun qilgandi. To'g'rimi? Boshidan уже compatibility.
Matematikani foundationi bo'lish uchun.
Ha.
Ya'ni hamma narsa mana shu orqali bo'lishi kerak matematikada. Foundationni matematikani fundament qilmoqchi edi.
Keyin Alan amaki qaraganda, bo'ldi, men o'zim lavashxonamni o'zim ochaman deb qo'pol qaytganda plus minus o'zini yo'nalishiga ketgan.
Urush uchun shunaqa vaziyat bo'lib qolgan. Urushda o'zi anaqasi bor, Enigma degan hack qilish kinosi.
Da, anavi imitation game bor.
Imitation game.
Juda zo'r kino. Mana bu. Benedict Cumberbatch. Ham rasmini kopiya qilib qo'yaylik. Alan Turing. Mana shu payti urushda anaqa qilaman deb adashib kompyuter yaratib qo'ygan. Biz Minecraft o'ynashimiz uchun.
Shunaqa.
Shu. Adash вообще borku bir o'tirib alohida bitta stream qilishimiz kerakda, shu haqida gaplashsak. O'ylaymanki, hozir turda qilmasdan sal soddaroq tushuntirsa bo'ladi. Masalan,
2da 2 qilib turib 2da bo'lib tushuntirsa.
Masalan, odam bor. O'rtada odam deylik. Odamni moshinlari bor. Ya'ni moshin degan kategoriya qismida qanaqa moshinlari bor, qanaqa uylari bor, qanaqa ishlari bor degandek aniq qilish mumkin. Ya'ni bir odamda bunaqa ishi bo'lsa, boshqa odamni bunaqa ishi bor degandek qo'pol qilib aytganda RPG qilib tushuntirsak bo'ladi. Nima deysiz?
Ya'ni misol uchun functionalda Alan Churchda 20 point ko'proq bo'lgan, bunda esa imperativda 20 point ko'proq bo'lgan RPG qilibmi?
Yo'q, point emas. Masalan, RPGda ham bittasi mag bo'lsa, bittasi anavi milishnik bo'lsa, ikkovi ham qo'pol qilib aytganda damak yetkazadi, bir-biriga uron yetkazadi, lekin yetkazish usuli har xil bo'ladi.
Fichalari bor.
O'zining fichasi bor. Shunaqaroq sifat tushuntirsak, harakat qilib ko'rsak bo'ladi.
Unga o'ylab ko'rish kerak, chunki hozir ba'zida bu narsani o'zimga o'zim tushuntirolmay qolaman-da, shuning uchun yaxshilab o'ylab ko'rish kerak.
Xuddi mana bu 7 yoshli odamga, 7 yoshli bolaga tushuntirgandek harakat qilamiz, qo'ldan kelguncha.
Tushunarli.
Shu davom etavering, uzr, bo'lmayman.
Ishqilib qisqacha qilib aytadigan bo'lsak, o'zi haqiqatan shuni tushuntirib ham keyin men chiqib ketaversam kerak. Qisqacha qilib aytganda, tiplar nega kerak? Shu tiplar programmani statik analiz qilib turib, formalniy verifikatsiyaning bir turi. Shu. Lambda calculus nega aynan lambda calculus? Chunki type theory rust-lang nega aynan lambda calculus? Nega? Chunki
TypeScript sucks.
Asos bo'ladi. ishqilib computation asosi bo'ladi, matematikani asosi bo'la olmagan taqdirda ham computation asosi bo'la olgan. Ya'ni bizda misol uchun substitutionlar, beta reductionlar, balobattarlar, mana shu lambda termlarni keyin tiplarga bo'lib, simplified lambda calculus keyin mana shu lambda termlarni ustiga tiplar yopishtirib boraveramizda. Ya'ni misol uchun hammasi уже lambda calculus klassika bu anunda. Ya'ni misol uchun Javada lambda calculus ishlatilmaydi. O'zini qanaqadir narsalarni o'ylab toptirishgan. C++ da bu narsa ishlatilmaydi. O'zicha misol uchun yangi narsalar o'ylab toptashalgan. Lekin computation bo'yicha fundament shuda. Shuning uchun ham type theory ham lambda calculusdan boshlanyapti. Keyin mana shunaqa lambda calculusga chunki ko'p narsani tagiga olib borib compile qilsa bo'ladi. Ishqilib lambda termlarni tipizatsiya qilishlargacha o'tamizda. Chunki hammasi bor lambda calculusda qolgandan keyin lambda calculus qanchalik darajada kuchli biladigan bo'lsak va o'shani qanchalik darajada navorot qilib boraveradigan bo'lsak, yangi tiplar qo'shib, polimorfik lambda calculus qo'shiladi. Keyin generikda bo'lishi mumkin. Shunaqa narsalar. Aynan nega lambda calculus shunaqa, nega type theory shuni tushuntirib o'tgandek formal verifikatsiya. Va nega misol uchun oddiy odamga kerakmi degan savol misol uchun.
Mana qilib qo'shilib boraveradi, to'g'rimi?
Qanaqa? Anaqami? Boya chizganimizdagi.
Mana ishqilib mana bunaqa. Ya'ni hech nimamiz yo'q. Bitta turshida o'tiribmiz, manada blatnoy bo'lib, hamma magazinga kirib chiqdik. Har bir magazinda o'zi qanaqadir turini qo'shadi-da. Abstraksiyasini nima osonlashtiradi.
Va tip ham powerful bo'lgan sari shuncha ko'p baglarni ushlab qolaveradi. Ishqilib shu kategoriya teoriya keyin bizga compositionality beradi. Type theoryni o'rgangandan keyin type theoryning har xil turlari bor. Ya'ni misol uchun homotopy type theory biladiganlarimiz bor. HOTT kichkina o bilan yoziladigan, katta o bilan yoziladigan hot bor. Higher order, higher observational type theory bor. Two level type theory qo'shiladi, 2 LTT. Hali bu ko'p type theorylar. Uning ustiga bu faqatgina dasturlashga emas, matematikaga ham foydali juda ham. Ya'ni type theory set theoryga o'xshab ketadi, lekin set theorydan farqi shundaki, set theoryda paradokslarni qilib qo'yish oson. Type theoryda paradokslar hal qilingan. Ya'ni misol uchun Russell paradoks type theoryda yo'q. Bu hal qilingan. Set theoryda unaqa paradokslar bo'lishi mumkin. Type theoryda ya'ni misol uchun tiplar unik bo'ladi, ya'ni bitta term har doim bitta tipga ega bo'ladi. O'shaning uchun Russell paradoks ham kelib chiqmaydi. Misol uchun adashmasam.
Bizda hali ring theory bor, group theorylar bor. Bu ham juda men bu qarangda, 4 ta roli bor-ku, 4 tamida roli. Group theoryni.
Uni bilmayman, lekin group theoryga uncha tushunmayman.
Set kimida? 4 ta roli. 4 rules of set theory. Laws. Identity, complement, commutativ, associativ, distributiv. Shunaqamida yo setmidi? Yoki group teoriyamida? Mana closure, associative, identity, inversiya. Laws of
inversiya degani, bunaqa narsani aniqlash uchun yaxshilab menimcha tayyorlanish kerak bu stringga va uni ustiga bobo she'r chaqirsa ham bo'ladi. Ular yaxshi tushunadilar.
Zo'r.
Odamga tushuntirish.
Zo'r. Anoni ko'rdim. Kimdir videosida real masalan qanday tushuntirsam bo'ladi. Bizda bor natural number raqamlar bor, naturallar. Anaqa edi. Natural numberlar bor, keyin integerlar keladi. Keyin rational to'xtang, Q edi, adashmasam.
Natural, integer, keyin ya'ni ikkita integerdan tashkil topgan dropni tepa-pastda ikkita integer bo'ladigan bo'lsa,
Q midi o'sha?
rational bo'ladi, Q bo'ladi. Keyin
real raqamlar.
Irrational, keyin real adashmasam.
Irrational qanaqa yozilardi?
Irrational tepa-pastda ikkita dropdan tashkil topmagan bo'ladi. ya'ni tepa pastda misol uchun любой rational numberni ikkita drop tepasiga bitta integer qo'shib yaratsangiz bo'ladi-da. Ya'ni lekin misol uchun p irrational hisoblanadi. Uni drop tepasiga bitta raqam qo'yib yasolmaysiz. U
Shunday. Anasi infinite bo'ladi hali. Keyin kompleks raqamlar bor. Shunaqamidi? Number theory, natural number, integer, deb ketaylik. Mana rational bor, irrational bor. Hammasi real numberga kiradi. Hozir men ustida kompleks raqamlar bor. Tak, real, complex.
Bu raqamlarni o'zi ham borib, anunga
Mana topdim. Mana. Qarang. Juda chiroyli rasm.
Hierarxiyasimi?
Juda chiroyli rasm. Mana shuni grup o'sha set teoremida grup emas edi, set teoriyada o'zini anosi bor edi, grafi bor edi. Qaysi grup bo'la oladi, bo'la olmaydi.
Shartlari qanaqadir propertyni satisfy qilish kerak.
Mana yana bitta chiroyli graf. Ana o'sha diagrammacha. Copy image. Mana yoniga tiqib qo'ydim.
Bunday misollar bor ekanda.
Mana rational number misoli bilan-da. Masalan, mana bu ham rational, mana bu ham rational. Mana bu irrational degani alohida mana bu joyda bor edi. Kichkinagina anochasi bor. Nima edi? Irrational degani bu ham mana dropli. Drop deganda mana bu nuqtadan keyin raqamlar bor. Faqat uni oxiri yo'q, to'g'rimi? Ya'ni 1 2 3 degan emas, u payga o'xshab tinimsiz ketaveradi.
Shunaqa. Yoki adashtirdim, to'g'ri turing. Realga pi kiradi.
Pi kiradi, lekin pi xuddi shunday irrational. Irrational bor. Xuddi mana bu tepadagi bor-ku mana. Stop. Realda rational, menga yana irrational bor. Bu aytganda. Qancha? To'xtang. Realda ichida rational, ichida integer, ichida natural va undan tashqari realda o'zida mana irrational desak ham bo'ladi, to'g'rimi? Alohida mana bunaqa dumaloqcha ichida.
Adashmasam shunaqa.
Mana kompleks raqamlar, ichida imaginary raqamlar ham bor ekan. Q quotient. Qayerda ko'rdim ha? Hozir men juda ko'rdim. Mana. Hoppa. Ko'rgan sari zo'r ketdi. Mana.
Ana.
Faqat bitta minusi, mana bu irrational emas, imaginary bo'lish kerak. Mana bu narsasi. To'g'rimi?
Hech qanday conventionlarni ham hech kim hurmat qilmaydi matematikada.
Shuning uchun aytdim-ku, matematika JavaScriptdan battardir.
Ijod qilib tashlashgan.
Ijod qilingan. Chunki bu yerda irrational bunaqa qimirlab ketdi bu. Hop. Hozircha shu joygacha o'rgandim dedik-ku. Yana nima qo'shsak bo'ladi? Prosta bitta chiroyligina video, qaysidir video ko'rgandim. Ko'rsatib berganda. Aynan qaysi raqamlarni gruppa qilishimiz mumkin emas.
And group
number theory and group theory yoki set theory. Set theory deyman, gruppa teoriya emas, set theoryda
set theoryda misol uchun magma degan narsa bor, adashmasam. Magmada ya'ni associative bo'lishi kerak. Misol uchun magma.
Hozir tablitsasini topaman. Table ida qanaqadir.
Ya'ni algebrada mana magma degan narsa bor edi. Abstract algebrada ekan mana. Groupoid. Group like, ring like, lattice like, module like, algebra like. A magma consists of a set equipped with a single binary operation that must be closed by definition. Shunaqa ish qilib. Zo'ranisi bor. Buni o'rganayotganda, semigruppani o'rganayotganda mana shundan qaragandim hozir. Paste qilaman. Mana. Magmaga associatsiya qo'shilsa semigruppaga aylanadi, semigruppaga identity qo'shilsa monoidga aylanadi.
O,
Reversibility qo'shilsa gruppa bo'ladi.
adashmasam
Magmaga
shu
divisible quasi
group
group.
theoryda. Yo, to'xtang. Men aytmoqchi bo'lgan narsam matematik operatsiyalar haqidamidi. Ishqilib shunaqangi narsa bor ediki, qarang. Shunaqangi narsa bor ediki, men sizga hozir ikkita narsani tushuntiraman. Ko'rganmiz, ko'rmaganmiz bilmayman. Plyus raqamimiz bor, minus raqamimiz bor, ko'paytirish bor,
Mhm.
bo'lish bor deylik. 4 ta amalimiz bor. Bundan tashqari boydaqa bizda natural raqamlar bor, keyin keladi integerlar. To'xtang. Как раз mana shu kategoriya grupga ham unga bog'langan. Adashmasam shu boyaga biratdan ko'rganman. Natural, keyin bu keladi, keyin bu quotient, real, complex, imaginary ishqilib mana bunaqa. Ya'ni birinchi imaginary, complex raqamlar. Qarang, mana bunaqa narsa. Boyaga 4 tami low bor. Bittasi identity, birinchisi symmetric anosi bor, adashmasam 0 anosi bor edi.
Transitivity.
Aha. Yana qaysidir bitta narsasi bor ediki, nimadir qilsa, agar mana shu 4 ta low'ni satisfy qila olsa, ya'ni bu gruppami yoki set hisoblanadi. Masalan, plyusli gruppasi bo'lishi mumkin, minusli gruppasi bo'lishi mumkin, ko'paytirish bo'lish. Plyusda adashmasam proof qilingan bor edi. Aynan mana shu videoni nimadir topolmayapman. Shuni o'ylab o'tiribman hozir.
Bilmadim lekin.
Hozir men yaxshilab qidirib ko'rayda.
Ya'ni misol uchun naturalda misol uchun plus ham refleksiv, ya'ni plus emas, ya'ni plus binary operationi refleksiv bo'lolmaydi. Ya'ni identity bunga tegishli emas. Symmetry lekin tegishli, ya'ni a plus b barobar b plus a simmetriya bo'ladi. Transitivity a plus b plus c barobar misol uchun a plus b plus c. Ya'ni qavslarga qaraydi.
Qara olmadi.
Ya'ni misol uchun simmetriya bo'luvda bo'lmaydi, chunki a ni b ga bo'lish bilan b ni a ga bo'lish farqi bor. Simmetriya bo'luvda bo'lmaydi. Mana shunaqa narsa, ya'ni buni chart qilsa bo'ladi. Ya'ni turbacha kattalarga bo'lib, kimda nima bor? Mana shuni kattalarga bo'lib chiqadigan bo'lsa, x lar qo'yib, ya'ni. Ya'ni misol uchun natural numberlarda simmetriya bor. Buni mana qilish kerak adashmasam. Mana qilsa to'g'ri bo'lardi. Natural integer
Qaytar ko'rsatyapsizmi? Ko'rinmayapti lekin.
mana
Stop.
chaprog'ida.
Hozir. Bo'ldi.
Va bu yerga pastga yozsak bo'ladi. Reflexivity, symmetry.
Siz yozib turavering, men ungacha qidirib turayda, uzr. Men topib olayda o'sha narsani, men topaman.
Keyin 3D bo'lishiga to'g'ri kelyapti-ya bu mana shuni. Plus, minus, ko'paytirib, bo'luv. Har bittasini alohida qilsak bo'ladi.
Set theory.
Qanaqa chart chizsam bo'lar ekan. Plus symmetric, ko'paytiruv symmetric. Plus transitive. Ko'paytiruv transitive. ya'ni simmetrik degani a plus b barobar b plus a. Transitivity degani tak a plus b plus c, adashmasam yo'q, bu ana edi. A plus b barobar c bo'lgan bo'lsa, implicationda a implies b bo'ladigan bo'lsa va esdan chiqib ketdi to'g'ri.
Lekin жесткий qo'tyapti mana bu Excalibur. Biz слишком ko'pmi deyman
Ha.
rasm-pasmlarimiz.
Bu implies c bo'ladigan bo'lsa, bu degani a implies c bo'ladi deganidir. Buni plusda tran of plus.
Plusda order of operation o'zgarmasligi ham shu xususiyatmidi?
Plusdami? Simmetriya order.
Symmetry order.
Orderimi? Orderi
To'g'ri, to'g'ri,
anaqa
to'g'ri, to'g'ri, to'g'ri. Symmetry.
distributivitysi bor.
Bo'ldi. Как раз hozir shu kursdagi narsangiz haqida aytmoqchi edim. Aynan shu narsa edi. Yana ikkita rule bor. Identity rule bor. Agar o'ziga teng, to'xtang. Identity emas, yo identity edi, yo 0 qo'shsa qaysi edi? Reflexivity'midi? O'z-o'ziga teng.
Reflexivity o'z-o'ziga teng degani.
0 qo'shsa
Identity
ham
bor degani.
qarang. 0 qo'shsa hech nima o'zgarmaydi degan narsasi identity.
Identity.
Ya'ni identity rule ham bor.
Identity.
Law bor.
U raqamga tegishli operatsiyaga bo'lmaydi.
Set theory,
binarniy operatsiyaga tegishli
reflexivity.
bo'ladi aniqroq. Binarniy bor, binarniga tegishli bo'ladi o'zi.
Tushundim. Distributivity.
Distributivity ya'ni misol uchun gruppalashda bu. Guruhlash.
Что-то kategoriya teoriyaga o'tib qoldikmi deyman.
Men unchalik tushunmayman lekin bu yerga. Group theory bunaqalarga.
Ozgina cooking talab qiladi.
We need to cook. Simmetriya shu. Transitivity cho'ta logikadagi sesimda raqamdagisi raqamda qanaqa ifodalasa bo'ladi mana shuni. Chunki
Qaysi narsani?
distributivity degani просто adashmasam a plus c barobar degani ko'rayaptim.
Yo'q, distributivity ko'ringan, reflexivity ko'rildi. A tenganga. O'zbekiston tengdir O'zbekistongamidi?
Ha, shu.
Bo'ldi.
Reflexivity deyiladi.
Order of operation doesn't matter degandek gapda, to'g'rimi? Qaysi
Distributive property over addition. Orderi muhim emas qolib plusda.
To'g'ri. Minusda bo'lmaydi, muhim bo'ladi.
Minusda yo'q.
Vot, minusda bo'lmaydi. Simmetriya minusda ishlamaydi. Vot, xuddi shu narsa edi. Xuddi shunaqa tablitsa bor ediki, mana bu raqamlarimizga ham bor edi. Masalan, natural numberda simmetriya yo'q. Adashmasam shunaqa edi. Ya'ni
Chiqilib menga 2 baho.
chiqishi yo'q. Hammamizga 2 baho.
Ha.
Maktabda o'qimaganmiz.
Adashmasam distributivity mana qayerda adashmasam. Ya'ni qavsdan tashqarida bo'ladigan bo'lsa, ko'paytirishga teng bo'ladi. Distribute qilish. Transitivity esa shu aytganimdek transitivity lekin implication boshqasini tushunchada hozir.
Mana bu zo'r beddizilgan rasmchani. Magma oxiriga keladi gruppaga, kvazi gruppalarga. Kimnidir ko'rdim yaqindagi anavi research qilayotgandi aynan shu kvazi gruppaga aloqador.
Quasi gruppa.
Associativity semi-gruppa bo'ladi, identity bo'lsa monoid bo'ladi, invertibility bo'lsa gruppa bo'ladi. Divisible bo'lsa mana bu degani ya'ni ikkova, ham associative, ham divisible bo'lsa unital magma bo'ladi, to'g'rimi? Yo'q. Associative quasi group. Mana bu narsani aytyapman, tepadagi. Qarang, mana bu nima?
Ha,
3-shoxchasi nima bu?
Bilmayman. Unital magma. Men o'yin tarafini bilaman faqat. O'yin tarafini. Asosiy semi gruppa, monoid gruppa.
Ha.
Quasi gruppada ham sal-pal tushungan joyim bor-da, hozir esimdan chiqib ketgan.
Identity bo'lsa loop, bo'lsa gruppa.
Har qanaqa lattice balobatlar narsalar bor bularning yana. Murakkab. Hech qilib bilmadim. O'rganmaganman hali.
Mana bu nima berasiz? Bunda bu vodkada bu hali, to'g'rimi? Mana bu shkalaga qarasak. Qaysi level
Bilaman.
berasiz? Masalan,
Bilmayman, lekin chunki bular basiclarida adashmasam qaysidir anini.
ya'ni bu
Basiclar emas endi.
pivocha deylik. Ana ranking bo'ladi-ku.
Ani zo'r bo'ldi lekin nima? Tier listni dodasi bo'ldi. S, A, B, C emas, endi mana shunaqa qilish kerak.
Mana bu Siga level. Yumshoqqina. Mana bu.
Bu F.
Narsani uchun. Mana bu adashmadan agar bu darajada aytadigan bo'lsa, bu pivo level ekan. Mana bu. Unchalik cooking emas.
Sistemasini.
Boyagi Church Rossmidi? Church Ross
Sierra Confluence.
Qozos. Church Ross. Church Rosser. Wait a minute. Church Rosserga bizga shunday qanaqadir spirit beramizmi? Или слишком абстрактно.
Gami?
Church
O'shani beraveramiz.
Rosser theorem abstraksiya bo'yicha. To'xtang, bunda hali mana bor. Qarang, masalan.
Ani qoldi. Undan bitta oldingisini desa bo'ladi.
Abstraksiya level bo'yicha bunaqa beramiz. Mana yerda kategoriya teori bor. Reально biz qanaqadir trash math stream qilsak bo'lar ekan. Mana bunaqa tier listlar qilib. Nima deysiz?
Vashni zo'r bo'ldi.
Bu ham mana bu Heisenbergmi? Shunaqa paytda universitetda o'sha matematika universitetida o'qimaganligimga afsus qilaman deydi-ku, kinolarda ko'rib. O'tirardik agar bitta universitetda o'qiganimizda, agar mana shu bitta gruppada.
Balkim. Avnosiga so'rashga misol professor bo'larmidi? Tushunmagan narsamizni.
Professor, help us grade this theory in the rank it. Ya mana metr zo'r bo'ldi.
Gap.
Trash math. Ya buni saqlab qo'yish kerak, saqlash kerak, definitely. Bizda oramizda Bobobekdan boshqa yana qanaqadir matematiklarimiz bormi?
Matematiklarmi yana? Muhammad aka deganlar va Alif Naut kanallarni biladigan bo'lsangiz, narsalar qiladi.
Yana matematiklar kerak. Bizda matematiklar tomonidan mana bunaqa cookery kerak. Cooking prosesi qiziq.
Yana Lazzat Abdullayevlar bor, ular endi chetda. Singapurda adashmasam. Zaza bilayotgani to'g'ri eslab qolman.
Xudo ularga
Yana
mana bu
matematiklar.
underground anavi qulay bo'lsa zo'r bo'lardi. Aynan bizga underground uchun kerak. Bizda real underground hisoblanar ekan, to'g'rimi?
Undergraduate'mi?
Yo'q. Graduate emas, underground. Ya'ni bilsangiz qanaqadir superstar anavi bor, gruppalar bor. Qarang. Superstar anavi bor, masalan, AC/DC deylik. Queen bor, to'g'rimi? Hamma taniydi.
Ha. Bandlar, ha.
Bandlar. Qanaqadir trash anavi sigaretchani chizib qo'yay, underground bor.
Ha,
Hech kim
anavi
tanimaydi.
Bochin anisi siz biladi. Bochi Drog'dagi.
Bilmayman, qanaqadir
Kestirma.
g'alati nom bo'ladi, bilmayman. Hech kim tanimaydi uni. 10 ta odam taniydi. Lekin o'sha 10 ta odam uchun mazza. Bizga kerak mana shunaqa leveldamizda hozir. Hech kimni degrisi bo'lmasa, hech kim anosi bo'lmasa, bizda anavi emas, fikrlarimiz mana bu Queen tomonga qarasak, вообще trashmiz. Yo'qmiz, non-existent.
No name.
No name'lamiz. Shuncha tipa underground mana bu yo'q.
Ha. Do'stlar, matematikda bizda kimlar bor? Guruhda Aziz borlar, anaqa Aziz username. Sohibjon o'rtalari. Type theory bo'yicha kuchlilar bor-ku. Haskell guruhda.
Mana.
Anna, University Underground.
Evet, shunaqa. Tirishlik bizni YouTube'imiz qani? YouTube'imiz topadi. Bundan deydi YouTube. Bizga kimdir kommentariyaga yozganmi nimadir deb, yo'q. Unutdi bizni. Bilmayman, to'g'risi zo'r ketdi. Vashshe maza qildim. Oy, vashshe meza. Voyla, rahmat, menim boray endi. Darcha siqilay notebookimga qarab. Rahmat sizga.
Sizga rahmat.
Yana stream qilib turamiz. Bundan tashqarida ishmasam boya aytganimdek stream qilamiz o'zimiz. Aynan mana underground math.
Yoki qanaqadir video chiqarsak bo'ladi.
Yo'q, videoga tayyorgarlik kerak-da. Biz masalan bir necha stream o'zimiz preparation qilsak, sekin masalan boshidan shakllanishni boshlanadi. Shakllanib bo'lgandan keyingina uni qanaqadir video qilib tarqatsak bo'ladi, demoqchiman.
Tushunarli.
Evet.
Hozirga o'xshab misol uchun ikki baholi anaqa nima tranzitsiyani bilmasdan o'tirganimda.
Eng qizig'ini aytaymi? Boyagi gapda superstarlar uchun biz trashmiz. Lekin bu narsa haqida bilmaydiganlar uchun biz superstar sifatida yana kelishimiz mumkin. Local superstarlar deylik. Lekin men yozibdi-da Zvizda. Bros doing big brain stuff deb yozdilar-da. Dilmurod bo'ladi.
10:28da.
Shuning uchun aytayman. Bu big brain tuyulishi mumkin, lekin aslida bu big brain emas. Endi qaysi tomondan qarashga bog'liq. Zo'r bo'ldi. 4 soat o'tirmiz. Yo'q, 3,5 soat ekan.
Yap.
Mayli, bu men streamni o'chirdim. Charchamay.
Bo'pti. Salomat bo'ling.
Shunaqa gap. Miyam pishib ketdi to'g'risi. Hammaga rahmat. Kelib turinglar, yozib turinglar kommentlar. Harakat qilamiz. Sizlar uchun deydi-ku. Men yaqinda uyda o'tirib qilaman adashmasam streamlarni kelajakda. Shunga uyda setup qilishni boshlayman sekin-sekin. Uyda qiladigan bo'lsam, bemalol kechasi bilan cooking qilaman mana bu TypeScript Night, Web 3 Night'larni boshlaymiz sekin-sekin. Anchadan beri so'rashyapti. Anchadan beri. Qiynalib ketishdi to'g'risi. So'rab Farruh aka so'rab qiynalib ketdi. Ishxonadaman kanishna. Ishdamiz. Shuning uchun uyga o'tkizish kerak sekin-sekin. Uyda bo'lsa kelin bolam kutib qolavermaydi har doim. Shuning uchun uyda bo'laman. Romni tiqdim. Vulkan oppoqqina edi. Moroshni to'kindi. Mayli. Charchamaylar, men yurdim. Bo'pti.